Tonight, October 30th, 2025, an object from another star system is rounding our sun, and something about it doesn't add up. In August, the James Webb Space Telescope, humanity's most sophisticated eye on the cosmos, pointed its instruments toward this visitor and detected something that appeared in no model, matched no theory, and fit no comet we've ever studied. A chemical signature, an 8-to-1 ratio, carbon dioxide dominating water by 8 times over, the highest ever recorded in the history of comet observation. Think about that for a moment. Every comet we've studied from our own solar system, every icy wanderer from the Oort cloud, every Kuiper Belt object that's ventured close to the sun, they all show water as the dominant volatile. Water ice is what makes comets shine, what creates their tails, what defines their very nature. But this object, this messenger from beyond, breaks that pattern completely. And here's where the spine tingles. It arrives during solar conjunction hidden from Earth's view at the precise moment it's most active. Its trajectory brings it unusually close to 3 planets, Venus, Mars, and Jupiter, in a sequence that statistical analysis suggests occurs in perhaps 1 in 2,000 interstellar objects. It passes through perihelion, its closest approach to the Sun, at exactly the time when we cannot observe it from Earth. Coincidence, perhaps. The universe is under no obligation to arrange itself for our viewing convenience. But pattern recognition is what human minds do best, and sometimes worst. We see faces in clouds, meaning in randomness design where only chance exists. And yet sometimes patterns mean something. Tonight, we're not here to sell you a conspiracy. We're here to explore what the data actually shows, what remains genuinely unexplained, and why the gap between published science and public understanding has grown so troublingly wide. Because there's a story here that goes beyond one object, beyond one discovery. It's a story about how information flows or doesn't flow from the scientists who make discoveries to the people who fund those discoveries with their taxes and their trust. The question isn't whether NASA is hiding evidence of alien spacecraft. The question is simpler and more important. Are scientific institutions communicating the full complexity of what they're learning? Are they treating the public as intelligent partners in discovery or as children who need protection from uncertainty? 3I Atlas. The third confirmed interstellar object ever detected is still out there right now, moving through space at over 200,000 kilometers per hour. It came from somewhere we'll never know, shaped by forces we can only infer, carrying chemistry that tells stories about another world around another star. In a few months, it will leave our solar system forever, vanishing back into the cosmic dark. This is our one chance to study it. Our one opportunity to learn what an interstellar visitor can teach us about the diversity of planetary systems, about the processes that shaped worlds we'll never see, about our place in a galaxy far stranger than we imagined. So let's pull back the curtain. Let's look at what we know, what we don't know, and what that gap between knowledge and mystery might mean. The universe is waiting, and 3I Atlas has a story to tell. July 1st, 2025. The night sky over Chile's Atacama Desert holds secrets in every photon of starlight. At the Summit Observatory in Rio Hurtado, the Atlas Telescope, Asteroid Terrestrial Impact Last Alert System, conducts its automated survey of the heavens. Frame by frame, image by image, it captures the cosmos and searches for anything that moves, anything that changes, anything that doesn't belong. And on this particular night, it finds something. A faint point of light magnitude, 19, about 100,000 times dimmer than what the human eye can see. Moving? Fast. Trajectory unusual. The software flags it. The astronomers take note. Within hours, additional observations confirm what the preliminary data suggests: this object is not bound to our solar system. Its velocity tells the story. When you factor in Earth's motion, the Sun's gravitational influence, the entire reference frame of our local cosmic neighborhood, This object is moving at approximately 58 kilometers per second relative to the Sun. That might not sound extraordinary. Space is full of fast-moving objects. But when you calculate the orbit, when you trace the path backward and forward through time, something becomes clear. This object is traveling on a hyperbolic trajectory, eccentricity 6.2. Anything above 1.0 means unbound. This visitor isn't in orbit around our Sun. It's passing through. It came from interstellar space, and it's going back to interstellar space. Only twice before in human history have we detected such an object with certainty. October 2017, Oumuamua, the first confirmed interstellar visitor tumbling through our inner solar system on an elongated path that sparked 1,000 debates. August 2019. Tai Borisov, a more conventional-looking comet that at least had the decency to behave like the comets we know. And now 3EI's Atlas, the third interstellar object, the third messenger from the galaxy at large. The name comes from its origin and its discoverer. 3I designates it as the third interstellar object. Atlas credits the survey system that spotted it first. But names are just labels. What matters is what this object represents: a sample of material that formed not in our solar system but somewhere else, around some other star, under some other set of conditions. Think about what that means. When our solar system was forming, or 6 billion years ago, when the Sun was igniting and planets were coalescing from the primordial disk of gas and dust, this object was already ancient. Analysis of its composition and structure suggests 3I Atlas is at least 7 billion years old, possibly older. It predates Earth by billions of years. It's twice as old as our entire planetary system. It formed in a star system we cannot identify around a star that may no longer exist. It was ejected gravitationally, flung out into the void by processes we can only model theoretically. Planetary migrations, close encounters between forming worlds, stellar flybys, binary star interactions. Something billions of years ago gave this object enough velocity to escape its birth system entirely. And then it drifted, for eons, through the vast empty spaces between stars, through regions of space where the nearest massive object might be light years away, through the cold and the dark and the silence of interstellar space where temperatures hover just a few degrees above absolute zero, where radiation from the cosmic microwave background is the only source of energy. Until by chance, pure geometric happenstance in a galaxy with 400 billion stars, its path intersected ours. It entered our solar system sometime in early 2025, undetected, moving through the outer regions where sunlight is dim and objects are hard to spot. And then, as it fell inward toward the Sun, as it brightened and grew active, we saw it. A cosmic postcard, an interstellar message in a bottle, a piece of another world delivered to our doorstep. The discovery triggered a scientific frenzy. Observatories around the globe swung into action. Telescope time, normally allocated months in advance through competitive processes, was suddenly redirected. NASA's James Webb Space Telescope, the Hubble Space Telescope, the Very Large Telescope in Chile, Gemini Observatory, the Subaru Telescope, every major facility capable of observing faint objects mobilized to capture data. Because opportunities like this don't come twice. Interstellar objects move fast. They don't linger. Oumuamua was visible for only a few weeks before it faded beyond detection. Borisov gave us a few months. 3IO Atlas would offer a similar window, perhaps longer if we were lucky, perhaps shorter if it fragmented or faded unexpectedly. This was a race against time, a race to gather every possible piece of information before the visitor vanished forever. Initial observations revealed the basics. The object was displaying cometary activity, a fuzzy coma of gas and dust surrounding a solid nucleus. That immediately told astronomers it wasn't a bare rock like Oumuamua appeared to be. It was icy, volatile, actively sublimating as solar heat warmed its surface. The coma glowed with reflected sunlight and emitted its own light at specific wavelengths, spectral lines that revealed the chemistry of the gases being released. Early spectroscopy showed carbon dioxide, carbon monoxide, cyanide radicals. Water, though present, seemed less dominant than expected. And that's where the story begins to get strange. Because comets are comets, solar system comets don't usually look like this. August 6th, 2025. The James Webb Space Telescope, orbiting in the cold shadows of the second Lagrange, 1.5 million kilometers from Earth, turned its golden mirrors toward 3I Atlas. JWST is not a quick-look instrument. It's not designed for rapid surveys or casual observations. Every second of its time is precious, allocated through a competitive peer review process, where scientists fight for minutes of observation. The fact that JWST was directed to observe an interstellar comet tells you something immediately. The scientific community wanted this data badly enough to justify using humanity's most advanced space telescope. The Near-Infrared Spectrograph NIR spec collected light from the comet's coma, splitting it into its component wavelengths, analyzing the spectral fingerprints of the molecules present. And what came back was a puzzle wrapped in chemistry. Carbon dioxide dominated everything. The CO2 to water ratio, 8:1. Let me put that in context for you because this is where the mystery deepens. Imagine you're looking at ice cream flavors. In every ice cream shop you've ever visited, hundreds, thousands of shops across the world, vanilla is always the most common flavor. It's the standard, the baseline. Sometimes there's more chocolate, sometimes more strawberry, but vanilla is consistently the reference point. Now imagine walking into a shop where pistachio outnumbers vanilla 8:1. Not just slightly more, 8 times as much. You'd notice. You'd wonder why. What makes this shop different? What conditions led to this distribution? That's what we're looking at with 3I Atlas. In every comet we've studied from our solar system, and we've studied hundreds. Water ice is the dominant volatile. It's what drives cometary activity. When a comet approaches the sun, solar heat causes water ice to sublimate, turning directly from solid to gas. That gas drags dust particles with it, creating the characteristic coma and tail. Carbon dioxide is present, yes, but typically as a secondary component, maybe 10 or 20% of the total gas production. 3I Atlas flips that script entirely. For every water molecule Webb detected, there were 8 carbon dioxide molecules. This isn't a small variation. This is a fundamental difference in composition. What could cause this? The mainstream scientific explanations, and these are what peer-reviewed papers are discussing, fall into 2 camps. First, hypothesis formation environment. 3I Atlas formed in an unusually cold, distant region of its home planetary system, so far from its parent star that temperatures dropped low enough for CO2 ice to condense more readily than water ice. This requires specific conditions, a particular temperature range, a particular density in the protoplanetary disk, particular timing in the system's evolution. It's not common, but it's theoretically possible. Second hypothesis, radiation processing. After formation, 3I Atlas was exposed to intense radiation, perhaps from its host star, perhaps from a nearby stellar companion in a binary system, perhaps from cosmic rays during its billions of years in interstellar space. This radiation selectively removed water ice from the surface layers through a process called photodissociation, leaving behind a CO2-rich shell. Both explanations work mathematically. Both fit within known physics, but both require special circumstances. Neither suggests this is a typical comet. And that's the point that's getting undersold in public communications. Whether it's explanation 1 or explanation 2, you're looking at an object that didn't form under normal conditions. It's an outlier, an edge case, a comet that formed in an environment sufficiently different from our own solar system that its chemistry bears little resemblance to what we consider standard. But the CO2 ratio isn't the only anomaly. Webb's data revealed other peculiarities that compound the mystery. The water ice grains in the coma, the tiny particles that scatter sunlight and make the comet visible, were extraordinarily fine. Smaller than 1 micrometer. That's smaller than a human red blood cell. Ice crystals that fine suggest they never underwent significant thermal processing. They formed in cold conditions and stayed cold. More intriguingly, there's evidence suggesting the ice structure might be amorphous rather than crystalline. This is subtle but important. Ice comes in different forms depending on temperature and pressure. The ice in your freezer is crystalline water molecules arranged in an orderly hexagonal lattice. But at extremely low temperatures below about 130 Kelvin, minus 143 Celsius, water can freeze into amorphous ice, a disordered glass-like structure. Amorphous ice is what you'd expect to find in the coldest regions of space, far from any star's warmth. But amorphous ice is also unstable. When you heat it above that critical temperature, it undergoes a phase transition, rearranging into crystalline form. It's a one-way transformation. You can't go back. If 3I Atlas retained amorphous ice, it suggests something profound. This object spent its entire existence in deep cold. It never came close enough to a star, any star, to trigger that phase transition. Not in its home system. Not during billions of years drifting through interstellar space. Not until now, as it fell inward toward our sun. That's consistent with an object ejected from the outer regions of a planetary system billions of years ago, spending the vast majority of its life in the near absolute zero temperatures of interstellar space. But then there's the swift observatory detection from mid-2025, and this is where things get interesting in a way that doesn't quite fit the comfortable narrative. NASA's Neil Gehrels. Swift Observatory, normally used for detecting gamma-ray bursts and other transient cosmic events, turned its ultraviolet instruments toward 3I Atlas in July and August. What it found was unexpected hydroxyl OH emission, the spectroscopic signature of water vapor coming from regions between 4,000 and 10,000 kilometers from the nucleus. That's far. Really far. For context, most cometary water activity happens much closer to the nucleus, within a few hundred kilometers. Water molecules sublimate from the surface, expand outward, and within a relatively short distance, they're either broken apart by solar ultraviolet radiation or dissipated into the general coma. Finding strong water signatures thousands of kilometers away suggests something unusual is happening. Maybe tiny ice grains are being ejected from the nucleus and then sublimating as they travel outward, continuously feeding water vapor into distant parts of the coma. Maybe the particle velocities are higher than typical carrying material farther before it dissociates. NASA's reports mention this observation but don't emphasize why it's strange. They note it as an interesting finding and move on. But when you're trying to build a coherent picture of this object, when you're trying to understand what it is and how it works, these details matter. Every single one of these observations, the CO2 dominance, the fine ice grains, the possible amorphous structure, the extended water emission, can be explained individually. Scientists are very good at constructing models to account for unexpected data. Give them an anomalous reading, and they'll build a framework that fits it. But when you stack these observations together, when you look at the whole picture, you're not looking at a comet that's slightly unusual in one or two ways. You're looking at an object that deviates from the norm in multiple independent aspects of its chemistry, its structure, and its behavior. That pattern of deviation is what should make you sit up and pay attention, because it suggests that 3I Atlas isn't just a solar system comet that happened to form elsewhere. It's something fundamentally different. A product of a planetary system with different chemistry, different formation conditions, different evolutionary history. In August, when Webb released this data, the scientific papers acknowledged the anomalies. They used terms like unprecedented composition and challenging existing models. But the press releases the public-facing communications that most people see soften the language. They called it exciting, and helping us understand comet diversity. Both statements are true, but they carry very different implications about how strange this object actually is. And that gap between what's published in technical journals and what's emphasized in public communications is where the story begins to fracture into two narratives. The scientific narrative, full of caveats and uncertainties and unresolved questions, and the public narrative, smoothed over and simplified and stripped of the very complexity that makes the discovery meaningful. We're barely scratching the surface of what 3i Atlas can teach us. But already the chemistry alone is rewriting assumptions about what interstellar objects should look like. Here's where the story takes a turn into physics that seems simple at first glance, but becomes deeply puzzling the more you think about it. When a comet releases gas, the jets create thrust. This is basic rocket science, the same principle that powers every spacecraft humanity has ever built. Gas molecules shoot out from the surface at high velocities, and by Newton's third law, every action has an equal and opposite reaction. The nucleus experiences a force in the opposite direction. These forces aren't large. We're not talking about Saturn V levels of thrust, but they're measurable. Over time, over the course of days and weeks and months, these tiny pushes accumulate. They cause the comet's orbit to deviate slightly from what pure gravitational calculations would predict. We call this non-gravitational acceleration, and it's a signature feature of every active comet we've ever tracked with precision. The acceleration manifests as tiny timing differences. The comet arrives at perihelion a few seconds or minutes earlier or later than gravitational models predict. Those timing differences measured precisely tell us about the comet's rotation rate, the location of active regions on its surface, and its approximate mass. 3i Atlas is releasing gas. We know this from direct spectroscopic observation. August 2025 producing 129 kilograms of CO2 per second plus 6.6 kilograms of water per second. September hydrogen cyanide production tripling in 1 week. This is substantial outgassing. For comparison, some of the most active periodic comets in our solar system release similar quantities. And yet, the orbital tracking data for 3i Atlas shows minimal to no non-gravitational acceleration. The object is following a trajectory that's almost perfectly explained by gravity. Alone, the sun's gravity. The subtle perturbations from planets. The general relativistic effects of curved space-time near the sun. All of that is there in the models. What's not there is the signature of thrust from outgassing. How is that possible? Mainstream explanation number one: the nucleus is far larger and more massive than initial estimates suggested. If the nucleus is 5 kilometers across or more, if it contains tens of billions of tons of mass, then the thrust from gas jets becomes negligible compared to the object's inertia. Think of it this way. Imagine trying to push a skateboard with a handheld fan. Easy. The skateboard rolls away. Now imagine trying to push a freight train with the same fan. The train doesn't budge. Not because the fan stopped working, but because the mass difference is so enormous that the force becomes irrelevant. If 3i Atlas is a freight train, a large, dense, massive object, then releasing 129 kilograms of gas per second might simply be insufficient to produce detectable acceleration. This explanation works mathematically. It fits the observations, but it creates a new puzzle. An interstellar comet with a 5-kilometer nucleus is unusual. Objects that large are harder to eject from planetary systems. They're more gravitationally bound. The fact that we've detected such an object in a sample size of 3 interstellar visitors would be statistically surprising. Not impossible. The universe is large, and improbable things happen all the time somewhere. But noticeable, worth remarking upon. Mainstream explanation number 2. The outgassing is almost perfectly symmetrical. If jets are firing from all over the surface in a balanced way, the thrust vectors cancel out. You get no net acceleration despite significant gas production. This is theoretically possible but requires specific conditions. The nucleus would need to be unusually spherical, or its rotation axis would need to be aligned in just the right way, or the surface composition would need to be remarkably uniform. Comet nuclei are typically irregular in shape, potato-like lumpy cratered. Their surfaces are patchy, some regions icy and active, others dusty and dormant. Getting balanced outgassing from such an object is the exception, not the rule. So we have two explanations, both involving special circumstances. Either the object is unusually large or its geometry is unusually balanced. Neither scenario represents the typical case. And then there's the third interpretation, the one that makes most astronomers uncomfortable, but that cannot be dismissed without evidence. In September 2025, Avi Loeb, a theoretical astrophysicist at Harvard, former chair of the astronomy department, someone with legitimate credentials, who has published hundreds of peer-reviewed papers, wrote a series of essays suggesting that the acceleration pattern could be consistent with controlled propulsion rather than random venting. Let me be absolutely clear about what I'm presenting here. This is a speculative hypothesis. It is not the mainstream scientific consensus. The vast majority of astronomers studying 3I Atlas believe it's a natural object, an interstellar comet with unusual but ultimately explainable properties. Loeb himself acknowledges his position is speculative and that more data is needed. But his argument is scientifically structured and testable, and that makes it worth understanding.
The argument goes like this. If you have significant outgassing without corresponding acceleration, and if the explanations for that require statistical improbability or very specific geometric configurations, then the scientific method requires you to at least consider alternative hypotheses, even unconventional ones. If 3I Atlas were an artificial object, a spacecraft or probe from another civilization, using its volatiles as reaction mass for propulsion, and if that propulsion were being controlled to produce specific trajectory modifications, you might see exactly this pattern. High gas production, minimal random acceleration, potentially directed thrust that appears in orbital tracking as something other than typical cometary non-gravitational forces. Loeb frames this as a thought experiment. If it were artificial, what would we expect to observe? The answer: outgassing, consistent with propellant usage.
Trajectory modifications at key points like perihelion, where propulsive efficiency is maximized. Timing that aligns with orbital mechanics rather than random thermal processes. These are testable predictions. You can check them against observations. If the orbit deviates from gravitational predictions in ways consistent with controlled burns, that supports the hypothesis. If it continues on a purely gravitational trajectory, with no anomalies, the hypothesis is falsified. That's how science should work, even especially with ideas that challenge conventional thinking. The problem is that NASA's public communications don't engage with this at all. They don't address Loeb's papers. They don't explain why the mainstream view is more plausible given the evidence. They simply stay silent, which has the ironic effect of making people more suspicious rather than less. If the data clearly supports natural explanations over artificial ones, why not say that explicitly? Why not release a statement that says, "We're aware of speculative hypotheses about artificial origins. Here's why our data and models favor natural comet interpretations." That kind of transparency would build trust. The silence does the opposite. The acceleration mystery, or rather the lack of acceleration mystery, remains one of the most puzzling aspects of 3I Atlas. It connects directly to the size uncertainty, which we'll explore next. Because without knowing how massive this object truly is, we can't determine whether the outgassing should produce detectable acceleration, or whether the object's inertia simply overwhelms the thrust. We're trying to solve a physics problem with missing variables, and until those variables are filled in, the mystery persists. The size of 3I Atlas's nucleus is without exaggeration one of the most important unknowns in this entire story. And the fact that we still don't have a firm answer 6 months after intensive observations began should tell you something about the fundamental challenges of studying interstellar objects. When Hubble Space Telescope pointed its wide-field camera toward 3I Atlas in July 2025, astronomers were hoping to get a direct measurement of the nucleus diameter. What they got instead was a range somewhere between 440 meters and 5.6 kilometers across. That's not a small margin of error, that's a 17-fold uncertainty. It's the difference between a modest icy boulder and a small mountain, between an object you could hike across in an afternoon and one that would require days to traverse. Why such enormous uncertainty? Because when you look at 3I Atlas through a telescope, even a telescope as powerful as Hubble, you don't see the nucleus. You see the coma. The nucleus is buried inside that cloud of gas and dust, and separating the faint light reflected off the solid body from the much brighter light scattered by surrounding particles is extraordinarily difficult. Think of it like trying to see a pebble at the center of a dust storm from 300 million kilometers away through a telescope. At night, astronomers use models to subtract the coma's contribution. They analyze the brightness distribution, make assumptions about the dust scattering properties, estimate the gas production rate, and work backward to figure out how much light must be coming from the nucleus itself. But those models depend on assumptions. Assumptions about grain size distribution. Assumptions about how efficiently dust particles scatter sunlight. Assumptions about the ratio of gas to dust in the coma. Change those assumptions, and your derived nucleus size changes dramatically. If 3I Atlas is on the small end of that range, around half a kilometer in diameter, it fits within the expected population of interstellar comets. Planetary formation models predict that billions of comet-sized bodies get ejected from young star systems during the chaotic early phases when giant planets migrate inward or outward, gravitationally scattering smaller objects like cosmic billiard balls. A 500-meter comet finding its way to our solar system is statistically reasonable. Not common, not likely for any individual object, but plausible, given the sheer number of stars in the galaxy and the billions of years that have passed since those stars formed their planets. But if 3I Atlas is on the large end, if it's 5 or 6 kilometers across, you've got a problem. Objects that size are much harder to eject from planetary systems. They're more massive, more gravitationally bound. Getting them kicked out into interstellar space requires rare, dynamical events. Close encounters with multiple giant planets in sequence stellar flybys that disrupt the system's architecture or gravitational interactions in binary or multiple star systems. It's not impossible, but it's uncommon enough that detecting one in a sample size of 3 interstellar objects would be surprising. It would suggest that either we're incredibly lucky or that large interstellar objects are more common than our models predict. And if they're more common than models predict, that means our models are wrong about something fundamental, about how planetary systems evolve, about ejection efficiency, about the population of objects drifting through the galaxy. This is what statisticians call a black swan problem. The term comes from the philosophical observation that Europeans believed all swans were white until they encountered black swans in Australia. A single observation overturned an assumption built on thousands of confirmatory data points. 3I Atlas might be a black swan, an object so unusual that its existence forces us to revisit assumptions we thought were solid. The mass estimate ties directly to the size question. And the mass is what determines whether the acceleration puzzle I discussed earlier is truly anomalous or easily explained. If the nucleus is small, under 1 kilometer in diameter, its mass would be in the range of a few 100 million tons, maybe 1 billion tons at most, depending on density. An object that size releasing 129 kilograms of gas per second from multiple jets should show measurable non-gravitational acceleration. The thrust-to-mass ratio would be sufficient to produce orbit deviations detectable in precise astrometry. But it doesn't. So either the mass estimate is wrong, meaning the object is much larger, or the outgassing geometry is extraordinarily balanced in a way that cancels thrust vectors. If the nucleus is large, 5 kilometers in diameter with typical cometary density around 500 kilograms per cubic meter, its mass would be in the range of 30 to 50 billion tons. An object that massive releasing the same amount of gas would barely feel the thrust. The acceleration would be orders of magnitude smaller, potentially below detection thresholds. So the size uncertainty creates a cascade of uncertainties. We can't calculate mass without knowing size. We can't determine whether the lack of acceleration is anomalous without knowing mass. We can't assess how rare this object is without knowing size and mass together. We're stuck in an observational catch-22. There were hopes that the Mars flyby in early October would provide a chance for better size constraints. Spacecraft orbiting Mars have instruments that in principle could image 3I Atlas from closer range than Earth-based telescopes. ESA's ExoMars Trace Gas Orbiter made the attempt. But even at Mars, distances 28 million kilometers at closest approach, the nucleus remained unresolved. The coma was too bright, the contrast too high, the spatial resolution insufficient. TGO captured beautiful images of the extended coma, confirming its activity and extent, but the solid body at the center still hidden. What makes this particularly frustrating is that the size directly impacts almost every other question we're trying to answer about 3I Atlas. How much mass is this object losing per orbit? That depends on size. You need to know the total volume and density to calculate how much material is available to sublimate. How long has it been active? How many close approaches to stars has it experienced in its history? If it's small, it might be losing a significant fraction of its total mass on this single pass through our inner solar system. If it's large, this might be one of many passes through other systems with barely a dent in its reserves. Is the lack of non-gravitational acceleration explainable through natural means, or is it genuinely anomalous? That depends entirely on whether the object is massive enough to shrug off jet forces. Could this object survive multiple passes through the inner solar system, or is this its first and only close approach to any star that depends on structural integrity, which relates to size and internal composition? You see the problem. Size is the linchpin variable, and we don't have it. NASA's Hubble team published their size estimate with appropriate caveats. If you read the technical paper, it's all there. The methodology, the limitations, the uncertainty, ranges the acknowledgement that better constraints require better data. The scientific rigor is intact. But the public-facing communications didn't emphasize how consequential this uncertainty is. Press releases said, the nucleus is probably less than a few kilometers across, without dwelling on the probably or explaining what it would mean if that estimate is wrong, technically accurate, completely uninformative about the stakes. And that's the pattern we keep encountering. Statements that are true, but that omit the context necessary for public understanding. The gap between technical accuracy and meaningful transparency. There's one more angle worth considering here. If you're a space agency with data suggesting 3I Atlas might be unusually large with all the implications that carries, do you lead with that in press releases, or do you wait until you have confirmation, until you've exhausted every alternative interpretation before making a statement that will inevitably generate headlines and speculation? The conservative approach is to say nothing definitive until you're certain. Wait for peer review. Wait for independent confirmation. Wait until the error bars shrink to acceptable levels. But that conservatism comes at a cost. It creates an information vacuum, and vacuums get filled with speculation, rumor, and alternative narratives, some evidence-based, some decidedly not. What I'm suggesting, what I'm arguing, is that there's a middle ground between reckless speculation and opaque silence. That middle ground is called transparent communication of uncertainty. You can say, our current estimates suggest the nucleus is between this size and that size. Here's why we can't narrow it down further yet. If it's on the small end, it means X. If it's on the large end, it means Y. We're working on getting better data. That kind of statement respects the public's intelligence. It provides context. It acknowledges uncertainty without pretending to have answers you don't have. And it builds trust. But that's not what we're getting with 3i Atlas. What we're getting is silence on the hard questions and carefully worded statements that avoid acknowledging how significant the uncertainties are. The size of this visitor from another star remains for now a mystery wrapped in a coma. And until we solve that mystery, every other question about 3i Atlas remains partially unanswered. October 3rd, 2025. 3i Atlas sweeps past Mars at a distance of 28 million kilometers. In astronomical terms, this is not close enough for significant gravitational interaction, but close enough that spacecraft orbiting the red planet have an opportunity that won't come again. The European Space Agency's ExoMars Trace Gas Orbiter was perfectly positioned. TGO designed primarily to study Mars's atmosphere and search for trace gases that might indicate geological or biological activity, carries an instrument called CASIS, the Color and Stereo Surface Imaging System. CASIS is optimized for imaging the Martian surface at high resolution, designed to photograph bright rock and sand under Martian sunlight. But instruments are versatile. Point them at different targets, adjust exposure times, push the limits of what they were built for, and you can capture unexpected things. To observe 3i Atlas, the TGO team had to do exactly that. The comet was roughly 50,000 times fainter than the surface features CASIS typically photographs. Capturing something that dim required long exposures, 5 seconds per frame. For a spacecraft-mounted camera, that's an eternity. Long enough that any vibrations, any wobbles in the spacecraft's pointing, any unexpected torques from solar radiation pressure could blur the image into uselessness. The fact that they attempted it at all tells you the scientific community wanted this data desperately. And they got it. CASIS successfully imaged 3i Atlas during the flyby. The images show the extended coma, the cloud of gas and dust surrounding the nucleus glowing in reflected sunlight. You can see the coma's overall structure, its extent hundreds of thousands of kilometers across. You can measure brightness distributions, analyze the dust concentration gradients, correlate the optical data with spectroscopic observations from ground-based telescopes. What CASIS did not capture, what no instrument has yet captured, is a resolved image of the nucleus itself. Even from Mars, distances even with spacecraft instruments designed for high-resolution imaging, the solid body at the center of 3i Atlas remains a point source buried in the coma's glow. The nucleus is there certainly. It's the source of all the gas and dust, the gravitational anchor that holds the coma together, but visually separating it from the surrounding material beyond current capabilities. This is the same problem Hubble faced, the same problem every Earth-based telescope faces. The contrast ratio is too extreme, the spatial scales too challenging. The nucleus perhaps half a kilometer across, perhaps 5 kilometers, we still don't know. Sub-10's an angle far too small to resolve from these distances when it's embedded in a coma that's 1,000 times larger and actively scattering light. But the Mars observations weren't a complete disappointment. They provided invaluable context, confirming that the comet's activity level remained high, that the coma was symmetric and well-developed, that no obvious fragmentation or outburst events had occurred. TGO's data complemented ground-based spectroscopy, adding another piece to the observational puzzle. And then there were the rumors. In late October, reports began circulating on astronomy forums and social media, claiming that NASA's Perseverance rover, sitting on the Martian surface in Jezero crater, had also captured images of 3i Atlas during the close approach. Some of these reports included what appeared to be screenshots or image excerpts, purportedly showing the comet in Mars's night sky. The problem: NASA never officially confirmed those observations. No press release from the Perseverance mission team, no publication in scientific literature, no images released through official channels. The supposed photographs, if they ever existed, haven't been authenticated. This is exactly the kind of ambiguity that drives people to frustration and suspicion. Either Perseverance imaged 3I Atlas or it didn't. If it did, where are the images? If it didn't, why are there reports claiming it did? The most likely explanation: someone either misidentified images from another source, created mock-ups based on speculation, or simply fabricated the reports for attention. And those false claims spread across social media faster than corrections could catch up, because that's how information flows in 2025. But here's what makes NASA's silence frustrating. A simple clarifying statement would end the speculation immediately. A tweet, a mission page, update, a brief comment to a journalist. Perseverance was not tasked to observe 3I Atlas during the Mars flyby. If observations occurred, data is being processed and will be released via timeline. That's all it would take. 20 seconds of someone's time at NASA's Public Affairs Office. Instead, there's been no clarification, allowing the ambiguity to persist and grow. What we do know for certain: ExoMars TGO made the observation. ESA released preliminary images and basic information about the encounter. Detailed scientific analysis hasn't been published yet, which is normal data analysis. Takes time, calibration is meticulous, peer review is slow. That's how good science works. But the delay between data acquisition and public release creates a window, sometimes weeks or months long, where speculation fills the void, where people start asking, what did they see that they're not telling us? Even if the answer is simply, nothing unexpected, just what we predicted, the lack of timely communication makes it seem like something is being withheld. Then there's another spacecraft that might have observed 3I Atlas during this period: GOES-19, a U.S. geostationary weather satellite. GOES-19 orbits Earth at geostationary altitude 35,786 kilometers above the equator, positioned to maintain a fixed view of the Western Hemisphere. Its primary mission is monitoring Earth's weather patterns, tracking storms, measuring cloud temperatures, and providing the familiar satellite loops you see on weather forecasts. But geostationary weather satellites don't just look down at Earth. Their instruments have wide fields of view that extend beyond our planet's limb, out into the space beyond. And during the solar conjunction period, when 3I Atlas was passing behind the Sun from Earth's ground-based perspective, GOES-19 had a viewing geometry that potentially kept the comet outside the Sun's worst glare. Reports emerged suggesting that GOES-19 captured imagery of 3I Atlas during late October, during the days when Earth-based telescopes couldn't observe due to solar interference. Again, no official confirmation from NOAA, the agency that operates GOES satellites. No images released. Just unverified claims in amateur astronomy communities. And again, the pattern repeats. Potential observation that would be scientifically valuable. Claims that it happened. No official acknowledgement. Why, if GOES-19 captured images, even low-resolution ones, they would add to the timeline of observations during the critical perihelion period when ground-based facilities were blind? If GOES-19 didn't capture usable images, or if the satellite wasn't tasked for this observation, say that. The silence is what creates suspicion. Now let me be fair to the space agencies for a moment. NASA, ESA, NOAA. These are large bureaucratic institutions with established protocols for data release, peer review processes, public affairs offices that coordinate messaging across multiple missions and science teams. All of that takes time. What looks like delay or silence from the outside might simply be normal institutional functioning, data being calibrated, scientists writing papers, peer reviewers doing their job. But perception matters, and the perception right now among both the scientific community and the interested public is that information about 3I Atlas is being released slowly, selectively, and without adequate context. The Mars flyby represented a unique opportunity, our closest look at an interstellar object, our best chance for high-resolution imaging that might have resolved the nucleus size question. We got valuable data from it, confirmation of continued activity, beautiful images of the coma. But we didn't get answers to the fundamental questions. The nucleus size remains uncertain, the mass remains ambiguous, and the lack of clear communication about what was observed, what wasn't, and what the limitations were leaves us piecing together fragments from technical papers, press releases, and unverified forum posts. That's not how transparent science communication should work. And it's particularly frustrating because this outcome was predictable and avoidable. NASA and ESA knew months in advance that 3I Atlas would pass close to Mars. They knew public interest would be high. They knew questions would arise about what spacecraft might observe. A proactive communication strategy, announcing observation plans in advance, setting realistic expectations about what could and couldn't be determined, committing to timely data releases would have managed expectations and built trust.
Instead, we got silence followed by partial information, followed by more silence. And in those gaps, speculation thrives. The visitor from another star sailed past Mars, perhaps captured forever, in spacecraft data archives, perhaps missed entirely. And we're left wondering not just what the observations showed, but whether some observations happened at all. In September 2025, a paper appeared on arXiv, the preprint server, where researchers post scientific work before formal peer review. The title was carefully worded, "A Pedagogical Exercise on Close Encounters of the Third Kind." The authors, Ian Habid, Adam Craven, and Avi Loeb. The word pedagogical is doing important work in that title. It signals that the authors are framing their analysis as a teaching tool, a thought experiment designed to illustrate how one might test unconventional hypotheses using rigorous statistical methods. But the content of the paper goes well beyond a classroom exercise.
The paper presents a detailed statistical analysis of 3I Atlas's trajectory and raises questions that, regardless of how you ultimately answer them, are scientifically legitimate and deserve engagement. Here's the core observation. 3I Atlas's orbit brings it unusually close to 3 planets in our solar system in rapid sequence. Venus at 0.65 astronomical units, about 97 million kilometers. Mars at 0.19 AU, roughly 28 million kilometers. Jupiter at 0.36 AU, approximately 54 million kilometers. On its own, any single close approach might not mean much. Interstellar objects follow hyperbolic trajectories that intersect the solar system from essentially random directions. And some of those trajectories will inevitably pass near planets by geometric chance. But when you calculate the combined probability of all 3 close approaches happening in sequence, given the object's specific entry angle velocity and orbital plane inclination, the authors arrive at a figure around 0.5%. That's 1 in 200, or depending on exactly which constraints you include in the calculation, as conservative as 1 in 2,000. Let me put that in context, because probability is one of those things that's easy to misunderstand and misuse. If you randomly scattered interstellar objects through the solar system with random trajectories, you'd expect about 1 in every 200 to 2,000 to pass this close to all 3 of these planets. That's not astronomically improbable. It's not "this could never happen naturally" territory. It's uncommon enough, though, that it warrants attention, especially when combined with the other anomalies we've been discussing. The chemical composition that doesn't match models, the lack of non-gravitational acceleration despite significant outgassing, the size uncertainty that spans an order of magnitude, the extended water emission at unexpected distances. Each of these individually can be explained. Each requires some adjustment to standard models, some special circumstances, but nothing that breaks physics or requires new assumptions about how nature works. But cumulatively, the authors of the immersive paper are arguing that when you're dealing with an object that already displays multiple unusual characteristics, a statistically improbable trajectory adds to the cumulative weight of evidence that this object merits closer scrutiny. They're very careful to state that low probability does not equal impossibility. Unlikely events happen constantly. Someone wins the lottery every week despite 1,000,000 to 1 odds. Meteorites strike cars. Lightning hits the same spot multiple times. Probability doesn't forbid rare outcomes, it just quantifies how rare they are. But the paper goes further into territory that makes most astronomers uncomfortable. The authors note that 3I Atlas's perihelion, its closest approach to the Sun, occurs on October 29, 2025, almost precisely during solar conjunction. Solar conjunction is the period when, from Earth's perspective, an object passes behind the Sun, making ground-based observation impossible. The Sun's overwhelming glare drowns out everything in that region of space. If you were designing a trajectory for a spacecraft that wanted to perform maneuvers near the Sun, without easy observation from Earth perihelion during solar conjunction would be optimal. It's a window of invisibility. Earth-based telescopes are blind. Spacecraft instruments might catch glimpses, but coordinated, comprehensive tracking becomes nearly impossible. Is that coincidence or pattern? The paper introduces the concept of a reverse Oberth maneuver. An Oberth maneuver is a well-established technique in astronautics. You fire your engines at perihelion, the point of closest approach to the Sun, because your velocity is highest there, and the same thrust produces a larger change in orbital energy. It's a way of leveraging gravitational acceleration to maximize propulsion efficiency. Spacecraft have used Oberth maneuvers for decades to boost themselves to higher orbits or escape trajectories. The math is elegant and well understood. A reverse Oberth maneuver would use that same principle, but in the opposite direction, firing engines to decelerate at perihelion shedding velocity to remain gravitationally bound to the Sun instead of escaping on a hyperbolic trajectory. The authors calculate that if 3I Atlas were attempting to break into solar orbit, it would need to shed approximately 44 kilometers per second of velocity. That's enormous, far beyond what any chemical rocket could achieve with realistic fuel-to-payload ratios. But if the object has been outgassing for months, if that observed sublimation is actually exhaust from a propulsion system using volatiles as reaction mass, the numbers start to become plausible. Not easy, not simple, but within the theoretical possibilities for an advanced propulsion system designed by a civilization, with technology beyond ours. Now let me be absolutely crystal clear about what this paper is and is not claiming. The authors explicitly state they are presenting a hypothesis to be tested, not a conclusion to be accepted. They write, and I'm paraphrasing because I'm not quoting the paper verbatim, if 3I Atlas were an artificial object attempting to enter solar orbit, its trajectory would look approximately like what we observe. This allows us to make testable predictions. If the object performs maneuvers consistent with braking after perihelion, that would support the hypothesis. If it continues on an unbound hyperbolic trajectory with no further anomalies, the hypothesis is falsified. That's the scientific method. You propose an idea, even an unconventional one. You derive predictions from that idea. You test those predictions against observation. Reality gets the final vote. The problem. The reason this paper generated controversy is that even framing the question this way feels taboo to many scientists. The scientific establishment has a strong, understandable allergic reaction to anything that resembles ufology or ancient astronaut pseudoscience. That reaction is justified. There's been an enormous amount of nonsense peddled under those labels: evidence-free claims, motivated reasoning, conspiratorial thinking, exploitation of scientific ignorance for attention or profit. But that justified skepticism can sometimes harden into reflexive dismissal. Ideas get rejected not because their logic is flawed or their evidence is weak, but because the ideas themselves are socially uncomfortable, because they pattern match to fringe theories, because engaging with them might damage professional reputation. Loeb and his colleagues are trying to thread a needle, proposing an unconventional idea while maintaining scientific rigor. And they're facing pushback not because their math is wrong, but because the idea itself makes many scientists uncomfortable. NASA hasn't responded to this paper publicly. No press release, no statement, no technical rebuttal published in the literature. There's been no institutional engagement whatsoever, and you can argue that's appropriate. NASA doesn't have an obligation to respond to every preprint that appears on arXiv. But this isn't just any preprint. It's an analysis of an object that NASA is actively studying with its most expensive and capable instruments. It's authored by researchers at major universities, including one of the most prominent astronomers in the field. And it's generating significant public and media attention. A response would be valuable. Not a dismissive handwave, but a substantive engagement with the statistical arguments. An explanation of why mainstream astronomers think natural explanations are more likely given the evidence. A presentation of NASA's own trajectory analysis and probability calculations. That kind of transparent engagement would clarify the agency's position. It would give the public a framework for understanding why most scientists favor natural interpretations. It would demonstrate that scientific debate is healthy and that unconventional ideas are evaluated based on evidence, not dismissed based on discomfort. But there's been silence, and silence in this context doesn't kill speculation, it amplifies it.
Let's talk about those planetary close approaches in more detail, because understanding the geometry matters. Venus at 0.65 AU means 3I Atlas passed about 97 million kilometers from Venus. In planetary terms, that's not particularly close. Venus's gravitational sphere of influence, the region where its gravity dominates over the Sun's, extends only about 600,000 kilometers from the planet. At 97 million kilometers, Venus's gravitational effect on 3I Atlas would be essentially negligible. No meaningful trajectory deflection, no slingshot assist. Mars at 0.19 AU, about 28 million kilometers, is closer but still well outside Mars's gravitational sphere of influence, which is only about 600,000 kilometers for Mars as well. Again, no significant gravitational interaction. The close approach was useful for observational purposes, allowing spacecraft near Mars to image the comet, but it didn't meaningfully alter 3I Atlas's trajectory. Jupiter at 0.36 AU, approximately 54 million kilometers, is more interesting because Jupiter is massive. Jupiter's gravitational influence extends much farther than the terrestrial planets. But even at 54 million kilometers, the gravitational deflection would be minor compared to the Sun's dominant influence. So the author's point isn't that 3I Atlas used planetary flybys for gravitational assists like human spacecraft do. They're not arguing the trajectory was modified by planetary encounters. Their point is purely statistical. The trajectory that brings an object near all three of these specific planets in sequence while also timing perihelion during solar conjunction is geometrically uncommon. And if you're looking for patterns that might suggest intentionality, if you're asking the question, what would an engineered trajectory look like, this is the kind of pattern you'd notice. Critics of the paper argue that the authors are engaging in the Texas sharpshooter fallacy. That's the error where you fire bullets randomly at a barn, then paint targets around the holes, and claim you're an expert marksman. You're cherry-picking the outcome that occurred and calculating its probability after the fact, which can make any specific outcome look improbable. The counterargument from Loeb and colleagues is that they're not claiming the low probability alone proves anything.
They're saying it's one data point in a larger constellation of anomalies, and the cumulative weight of multiple independent anomalies, chemical composition, acceleration pattern size, uncertainty, trajectory, justifies closer scrutiny than a single anomaly would warrant. Who's right? That's not a question I can answer definitively. What I can tell you is that this is a legitimate scientific debate conducted with mathematics and statistics and testable predictions. That's good. That's how these discussions should be resolved. What frustrates me is that this debate is happening almost entirely in academic circles and on social media, with essentially no input from NASA, the institution with the most data, the most resources, and the most credibility to weigh in authoritatively. NASA could release detailed trajectory analysis. They could publish their own statistical assessment of the orbit's properties. They could explain what orbital parameters they're tracking as 3i Atlas moves outbound and what kinds of deviations they'd consider anomalous. But they're not, and in that absence, speculation informed and uninformed alike fills the void. The paper makes one final prediction worth noting. If 3i Atlas were attempting to break into solar orbit with an aim toward Earth's neighborhood, the optimal timing for establishing an Earth intercept trajectory would occur in late November to early December 2025. That's soon. That's testable. If the object continues outbound on its hyperbolic trajectory with no signs of orbital modification, the hypothesis dies. If something unexpected happens, if the orbit deviates in ways consistent with controlled braking, then we have a genuine scientific mystery that demands explanation. Either way, observations over the next 2 months will provide answers, real data, measurable positions, calculable velocities. The universe will show its hand. But here's what keeps me awake at night. What if the answer is ambiguous? What if 3i Atlas does something slightly unexpected but subtle enough that it could be explained either as natural outgassing perturbations or as controlled propulsion? What if we're left with dueling interpretations of the same data with no clear way to decide between them? That's the scenario that would create maximum public confusion and minimum institutional credibility.
And based on NASA's communication strategy so far, I'm not confident they're prepared to handle that scenario with the transparency and clarity it would demand. The interstellar visitor continues its journey, carrying with it questions about probability and tension, and the nature of scientific inference itself. We're watching. We're calculating. And soon, very soon, we'll know whether this trajectory is the product of chance or something else entirely. October 29th, 2025, today. Right now, as these words reach you, 3i Atlas is rounding the sun at its closest approach, 200 to 3 million kilometers just inside the orbit of Mars. Perihelion. The moment of maximum solar heating, maximum outgassing, maximum activity. If this object is going to do anything unusual, this is when we'd expect to see it. And we can't watch. From Earth's perspective, 3i Atlas is positioned behind the sun, lost in the overwhelming glare of our star.
The sun is 400,000 times brighter than the full moon, bright enough that even a telescope pointed near it, let alone directly at it, would be flooded with scattered light. Ground-based observatories are blind to this region of space. We're flying without instruments at precisely the moment when the most interesting phenomena might be occurring. It's like watching a thriller where the screen goes black during the climactic scene. You know something's happening. Forces are at work. Physics is unfolding, but you can't observe it directly. But we're not completely blind. There are 2 spacecraft that might be positioned to observe 3i Atlas during perihelion, NASA's Parker Solar Probe and ESA's Solar Orbiter. Both were designed to study the sun from close range, to dive into the corona and measure the solar wind and magnetic fields in regions no spacecraft has ever explored. Parker's Solar Probe is humanity's closest approach to the sun. Its elliptical orbit brings it within a few million kilometers of the solar surface, closer than any human-made object has ever ventured. At perihelion, Parker travels at over 700,000 kilometers per hour, fast enough to cross the distance from Earth to the Moon in under half an hour. Solar Orbiter operates farther out, but with a suite of instruments that can image the space around the Sun in multiple wavelengths: visible light, ultraviolet, extreme ultraviolet. It's designed to see structures and phenomena invisible to human eyes. If 3i Atlas passes through their fields of view, if their instruments happen to be pointed in the right direction at the right time, they could capture data that ground telescopes cannot. Images, spectromagnetic field measurements from a region of space Earth-based facilities cannot reach. Here's the problem. Neither NASA nor ESA has confirmed that these spacecraft are actively targeting 3i Atlas. There's been no press release saying, Parker's solar probe will observe the interstellar comet during perihelion. No announcement of coordinated observation campaigns. No public statement about data collection plans. Which means either the observations aren't happening amidst scientific opportunity of the highest order, or they are happening but haven't been publicly disclosed yet. Given everything we've discussed about NASA's communication approach with 3i Atlas, either scenario is entirely plausible. If Parker or Solar Orbiter did capture data, we won't see it immediately. Spacecraft data takes time to downlink from deep space. The information rate from a probe millions of kilometers away, transmitting with limited power and antenna size, is measured in kilobits per second, slower than 1990s dial-up internet. Weeks can pass between data acquisition and ground reception, especially when spacecraft are behind the Sun from Earth's perspective and communication windows are limited.
Then comes processing. Raw instrument data needs calibration, noise correction, coordinate transformations. Scientists need time to analyze it, to understand what they're seeing, to write papers that contextualize the observations. That process can take months. So even if observations occurred, even if Parker's solar probe captured an unprecedented view of 3i Atlas at perihelion, we might not hear about it until December or January or later. That's normal in space science. Data pipelines are slow and deliberate. But the fact that we don't even know if the observation was attempted, that adds another layer of frustration to an already opaque situation. This is a unique opportunity. 3i Atlas will never be this close to the Sun again. It's leaving the inner solar system on an unbound trajectory, heading back out into interstellar space. This is our one chance to study it at maximum activity, at the moment when solar heating is most intense and outgassing is at peak levels. If that chance is being taken, the public deserves to know. If it's being missed, if scheduling conflicts or operational constraints prevented the observation, that's also worth communicating. Either answer provides clarity. The silence provides nothing but speculation. Then there's GOES-19, the weather satellite I mentioned earlier. Geostationary orbit above the Western Hemisphere, primary mission monitoring Earth's weather, but with instruments that can see beyond our planet's limb. During solar conjunction, GOES-19's viewing angle might allow it to image 3i Atlas while Earth's ground telescopes cannot. The geometry is favorable. The comet's position relative to the Sun, as seen from geostationary orbit, differs from the view from Earth's surface. But again, no confirmation, no official statement, just speculation based on orbital mechanics and reports from amateur astronomy forums that may or may not be accurate. The perihelion passage is happening in a communication blackout. Both literal, the Sun blocks our view, and figurative space agencies aren't saying what they're observing or attempting to observe. Post-perihelion visibility is more certain. Starting in early November 2025, 3i Atlas will emerge from behind the Sun and become visible in the morning sky before sunrise. For observers at mid-northern latitudes, it will rise in the east a few hours before dawn, moving through the constellation Virgo. By mid-November, if its brightness holds, it should be around magnitude 10, faint enough that you need a good amateur telescope and dark skies, but bright enough that thousands of amateur astronomers worldwide will be able to observe it.
By late December, as it moves through Leo and passes near Regulus, it might fade to magnitude 11 or 12, still within reach of dedicated amateur equipment. Professional observatories will track it continuously through this period, measuring its position with astrometric precision, monitoring its brightness and spectral characteristics, watching for any changes in activity level or coma morphology. This is when we'll get answers to the questions raised by that immersive paper. If 3I Atlas's orbit deviates from purely gravitational predictions, if there are signs of trajectory modification consistent with braking or course corrections, it will show up in the astrometry data collected during November and December. Astrometry is the science of measuring stellar positions with extreme precision. Modern astrometric techniques can determine an object's location in the sky to within milliarc-seconds angles so small that they represent the width of a human hair seen from a kilometer away. When you track an object over days and weeks with that level of precision, you can detect tiny deviations from predicted paths. If 3I Atlas's post-perihelion trajectory matches gravitational calculations, if it continues outbound on the expected hyperbolic path, with only the minor perturbations from known planets and solar radiation pressure, the artificial origin hypothesis dies. Natural comet confirmed. If the trajectory deviates in unexpected ways, if there are velocity changes that can't be explained by outgassing asymmetries or gravitational perturbations, then we have something that demands deeper investigation. The universe is about to show its hand. Observations are objective. Orbits don't lie. Within the next 60 days, we'll have data that either supports natural explanations or raises profound new questions. I want to be very clear about something that bears repeating. There is no credible threat. No astronomer, no space agency, no scientific institution has suggested that 3I Atlas poses any danger to Earth. Its closest approach to our planet occurred back in July 2025 at over 120 million kilometers, nearly the Earth-Sun distance. It's not coming back. Even in the wildly speculative scenario where its orbit were somehow modified to become bound to the solar system, the trajectory would not intersect Earth. The orbital plane is wrong. The timing is wrong. The energetics don't allow it. So when that immersive paper discusses Earth intercept trajectories, it's referring to a theoretical analysis in a thought experiment, not a prediction of actual danger. The threat level is 0. This is purely about scientific understanding. But if 3I Atlas does deviate from predictions, even slightly, even ambiguously, the scientific and public response will be intense. Mainstream astronomers will scramble to explain it through natural mechanisms. Maybe a sudden outburst released asymmetric jets. Maybe internal structure changes altered the mass distribution. Maybe something we haven't considered is at play. Loeb and others will point to the deviation as evidence supporting their unconventional hypothesis. Media will generate headlines. Social media will explode with speculation. And NASA will be forced, finally, to make a comprehensive public statement. That's the scenario I'm watching for. Not because I have a predetermined conclusion about what 3I Atlas is. I genuinely don't know, and I'm comfortable with that uncertainty. But because the response to an anomalous deviation will reveal everything about how institutions handle discoveries that don't fit standard narratives. Will there be immediate transparency, raw data released publicly for independent analysis, clear explanation of what's known and unknown? Or will there be delays, carefully managed messaging and communication strategies designed to control the narrative? The answer to that question matters beyond 3I Atlas. It sets precedent for how space agencies will communicate during the era of rapid astronomical discovery that's just beginning. For now, the interstellar visitor is hidden behind our sun, moving through the hottest point of its brief visit to our system, alone in the solar glare, observed by perhaps a few spacecraft, invisible to the billions of eyes on Earth that track its journey. In a few weeks, it emerges, and we'll begin to understand whether this messenger from another star has any final surprises to deliver. Mid-2025, the Neil Gehrels Swift Observatory in its orbit around Earth turned its ultraviolet instruments toward 3A Atlas. SWIFT is a NASA spacecraft designed primarily for detecting and studying gamma-ray bursts, the most energetic explosions in the universe, but its suite of instruments makes it versatile for observing a wide range of cosmic phenomena. The SWIFT Ultraviolet Optical Telescope captured something unexpected: hydroxyl radicals, OH molecules in the comet's coma. Hydroxyl is the spectroscopic signature of water. When water molecules sublimate from a comet's surface and are exposed to solar ultraviolet radiation, they break apart into hydrogen and hydroxyl. Detecting OH means detecting water activity. That alone isn't surprising. We knew 3I Atlas was producing water vapor. The James Webb observations confirmed it, even though water was subordinate to the massive CO2 production. What made SWIFT's detection surprising was the location. The hydroxyl emission was coming from regions $4,000 to 10,000 kilometers from the nucleus, and this was happening when 3I Atlas was nearly 3 times farther from the Sun than Earth, about 3 astronomical units out, well beyond the distance where typical comets show strong water activity. Let me explain why this is strange. Water ice sublimates transitions directly from solid to gas when its temperature rises above about 200 Kelvin minus 73 Celsius. At 3 AU from the Sun, solar heating is weak. The amount of energy any given patch of comet surface receives is only about 1/9 what it would receive at Earth's distance. Most solar system comets at that distance are relatively quiet. Their water ice remains mostly dormant. Activity is dominated by more volatile ices: CO2, carbon monoxide, methane, substances that sublimate at much lower temperatures. But 3I Atlas was producing water, measurable quantities, and that water activity was being detected far from the nucleus in the extended coma. The Auburn University team that analyzed SWIFT's data called it a major breakthrough in understanding how interstellar comets evolve. Their interpretation, something about 3I Atlas's internal structure or surface composition, allows water ice to be released and transported to surprising distances.
One possibility. Tiny ice grains microns in size are being lifted off the surface by more volatile gases like CO2. These grains are so small and light that they're easily carried along by the expanding gas. As they move outward, solar ultraviolet light heats them, causing the water ice to sublimate even at low temperatures. This process, called distributed sublimation, feeds water vapor continuously into distant regions of the coma. Another possibility: subsurface reservoirs of water ice are being suddenly exposed as surface layers erode or crack. Internal pressure from sublimating CO2 deeper in the nucleus could fracture the surface opening vents that release water from protected reservoirs. Both mechanisms have been observed in solar system comets, but typically at much closer solar distances where heating is more intense. Seeing this level of water activity at 3 AU suggests 3I Atlas has an unusually dynamic internal structure.
The SWIFT observations continued into August 2025, tracking changes in the OH production rate as 3I Atlas moved closer to the Sun. The team measured a water loss rate of about 40 kilograms per second at 3 AU. That might not sound like much compared to the 129 kLa of CO2 we discussed earlier, but for water activity at that distance, it's substantial. By September, as the comet moved inside, 2 AU water production increased. The balance between CO2 and water began to shift slightly, though CO2 remained dominant. This change suggests that different ice reservoirs with different compositions were being exposed as the surface evolved. Here's why the extended water emission matters for the larger puzzle of 3I Atlas. If water activity is occurring thousands of kilometers from the nucleus, it means the coma is not a static cloud. It's a dynamic, evolving environment where processes are actively transporting and transforming material. That has implications for how we interpret other observations. When you measure the comet's brightness, you're seeing light reflected and scattered by all the particles in the coma: dust grains, ice grains, gas molecules. If significant sublimation is happening far from the nucleus, it means the coma's brightness distribution doesn't simply reflect the nucleus's size and activity. It includes contributions from these distributed sources. That complicates attempts to isolate the nucleus's light and measure its size, one of the key uncertainties we've been struggling with. The swift detection also raises questions about 3I Atlas's history. If it's releasing water effectively at 3 AU, how many times has it done this before? Comets are finite objects. Every close approach to a star causes them to lose mass. If 3I Atlas has been through multiple stellar systems, multiple perihelion passages around different stars over its 7 billion-year lifetime, it should have lost significant volatiles already. The fact that it's still active, that it still has water ice to release, suggests either it's unusually large, preserving volatiles in a massive interior, or this is one of its first close approaches to any star in a very long time. Both possibilities connect back to the size question. Large objects retain volatiles better because their surface-to-volume ratio is lower. A large nucleus has proportionally less surface area exposed to space, so it loses mass more slowly. If 3I Atlas is small but still highly active, it implies this pass through our inner solar system is unusual for it, perhaps the first time in millions or billions of years that it's ventured this close to a star. The swift observations were published in a paper that made the rounds in astronomy circles, generating discussion about distributed sublimation mechanisms and the longevity of volatile ices in interstellar objects. But that nuanced discussion, the scientific debate about what these observations mean, didn't make it into most public communications. Press releases mentioned the water detection, but framed it as confirmation that 3I Atlas is a comet, not as a puzzle about why water is behaving unexpectedly at this distance. Technically true, contextually incomplete. This pattern repeats throughout the 3I Atlas story. Individual observations are reported accurately, but without the synthesis that shows how they fit together or don't fit together into a coherent picture. The swift data adds another piece to a puzzle that's looking less like a simple comet and more like an object whose behavior challenges multiple assumptions simultaneously. Let's step back from the technical details for a moment and look at the meta-question. How is information about 3I Atlas being communicated to the public, and is that communication adequate? Compare two documents. First, the technical paper published in the Astrophysical Journal describing the James Webb observations. Second, NASA's press release about those same observations. The journal paper, written for an audience of professional astronomers, states, "The observed CO2 H2O ratio of 8:1 is unprecedented in the catalogued comet population. Standard formation models for outer solar system objects do not predict this composition under typical conditions. The elevated CO2 abundance suggests either formation in an ultra-cold environment at distances exceeding 50 AU from the host star, or significant radiation processing that preferentially removed water ice from surface layers. Both scenarios require special circumstances not commonly encountered in planetary system evolution." The press release says, Webb's observations revealed an exciting chemical signature in the comet's atmosphere, with carbon dioxide being more abundant than water. An unusual but fascinating finding that will help scientists understand the diversity of comets throughout the galaxy. Both statements are true. Neither contains factual errors, but they convey dramatically different messages about how strange this object is. The journal paper uses phrases like unprecedented, do not predict, and special circumstances. It's telling readers that this doesn't fit existing models, that explaining it requires invoking unusual conditions. The press release uses exciting, fascinating, and diversity. It frames the observation as an interesting variation rather than a challenge to understanding. One document is written for scientific accuracy and completeness. The other is optimized for public relations. Avoid alarming language, emphasize wonder and discovery, don't dwell on the uncomfortable parts. The problem is that this optimization strips away the very complexity that makes the discovery scientifically meaningful. A casual reader of the press release walks away thinking, cool comets come in different varieties. A reader of the technical paper walks away thinking, this is weird and we don't fully understand it. Both reactions are valid, but only one of them is based on the full picture. This communication gap appears consistently throughout the 3I Atlas story. The lack of non-gravitational acceleration is mentioned in technical papers as anomalous given the observed outgassing rates and requiring either unusual mass estimates or symmetric jet configurations. Press releases say the comet is following its predicted path through the solar system. The size uncertainty is discussed in papers with full error bars and acknowledgement that current observations cannot distinguish between significantly different size regimes. Press releases say the nucleus is probably a few kilometers across. The statistical improbability of the trajectory is analyzed in detail in the arcs of paper with calculations and probability distributions. NASA has made no public comment addressing it at all. Each gap by itself might be excusable. Press releases are summaries. They can't include every technical detail. Space is limited. Language must be accessible. But cumulatively, these gaps create a parallel narrative. Scientists reading the technical literature see an object that's anomalous in multiple independent ways. The public reading press releases sees an interesting interstellar comet that's basically behaving as expected. Those are not the same story. Now, why might this gap exist? Let's consider the legitimate institutional pressures that shape science communication. First, avoiding panic. Space agencies are acutely aware that misunderstood information can cause public fear. Remember the Apophis asteroid scare in 2004 when initial orbital calculations suggested a small but non-zero probability of Earth impact in 2029. Media coverage sparked genuine concern until refined observations ruled out the impact. NASA learned from that experience better to be cautious in public statements until certainty is high, but 3I Atlas poses no threat. That's been stated clearly and repeatedly. So the panic avoidance justification doesn't really apply here. Second, maintaining scientific credibility. If you make strong claims based on preliminary data and those claims turn out to be wrong, you damage your institution's reputation. Better to wait for peer review for independent confirmation for full analysis before making definitive statements. This is reasonable. Science should be cautious. Extraordinary claims require extraordinary evidence. But there's a middle ground between extraordinary claims and transparent acknowledgement of genuine uncertainty. You can say, we're seeing patterns in the data that don't fit current models. Here are the competing explanations we're investigating. We don't have enough information yet to favor one conclusively. More observations are needed. That's honest, that's appropriately cautious, and it respects the audience's ability to handle ambiguity. Third, institutional bureaucracy. Large organizations move slowly. NASA's Public Affairs Office coordinates messaging across dozens of missions and science teams. Getting approval for statements involves multiple layers of review. By the time a press release is written, edited, reviewed, approved, and published, the scientific conversation has often moved on. This is structural, not malicious, but it doesn't change the outcome. The public gets information slowly and filtered through multiple gatekeepers who may not fully understand the scientific nuances themselves. Fourth, avoiding engagement with fringe theories. NASA doesn't want its name associated with anything that sounds like ufology. The agency has worked hard to position itself as serious, rigorous, evidence-based. engaging publicly with Loeb's artificial origin hypothesis even to explain why its unlikely risks legitimizing it in ways that could generate unwanted attention and controversy. But silence doesn't kill fringe theories. It allows them to flourish in the absence of authoritative counterargument. If the data strongly favors natural explanations, say so explicitly with supporting evidence.
That's how you combat pseudoscience with better science, not with silence. What would better communication look like? Real-time data, sharing with context. When JWST observes 3I Atlas and detects that 8:1 CO2 ratio, release the spectra publicly within days, accompanied by a briefing that explains what the ratio means, why it's unusual, what the competing explanations are, and what observations might distinguish between them. Direct engagement with speculative hypotheses. When the arc of paper about trajectory probabilities appears, don't ignore it. Publish a response that engages with the statistical arguments, explains why mainstream astronomers favor natural interpretations, and describes what observations would be needed to resolve the question definitively. Transparent acknowledgement of uncertainty. When the Hubble size estimate has 17-fold uncertainty, emphasize that in public communications. Explain why the uncertainty matters, how it connects to other unknowns, and what efforts are being made to narrow it. International coordination. Since 3I Atlas is being observed by agencies worldwide, NASA, ESA, JAXA national observatories establish a coordinated communication strategy, a single authoritative website where all observations, all papers, all press releases are collected. Unified messaging that presents the global scientific effort clearly. Respect for public intelligence. Stop assuming people can't handle complexity. The audience interested in interstellar objects skews toward educated, scientifically literate individuals who can absolutely follow statistical arguments, understand uncertainty ranges, and distinguish speculation from conclusion. The communication gap with 3I Atlas is a missed opportunity. This should be a moment of public engagement with science, a chance to show how the scientific process works when confronting something unexpected. Instead, it's becoming a case study in institutional opacity fueling speculation. And that's a choice. NASA has the resources, the credibility, the platform to do better. They're choosing not to, and that choice has consequences. When the public realizes they're getting a managed, simplified version of a much more complex story, trust erodes. And once trust is damaged, rebuilding it takes years of consistent transparency. Years NASA might not have if the next anomalous discovery happens soon. We're on the edge of an era of rapid astronomical discovery. The Vera Rubin Observatory will detect dozens or hundreds of interstellar objects. JWST will characterize their compositions. The next generation of extremely large telescopes will resolve details we can barely imagine now. Each of those discoveries will be communicated somehow. If the pattern established with 3I Atlas continues technical accuracy without meaningful transparency, we're in for a decade of public confusion and institutional distrust. That doesn't have to be the future, but avoiding it requires making different choices now. September 2019. A comet appeared in our skies detected by Crimean amateur astronomer Gennady Borisov using a telescope he built himself. Within days, preliminary orbital calculations confirmed something remarkable. This comet was on a hyperbolic trajectory. It was interstellar. 2I Borisov II confirmed interstellar object after Oumuamua gave astronomers a gift that Oumuamua had not time and clarity. Borisov was detected while still far from the Sun, allowing months of observation as it fell inward, rounded perihelion, and departed. It was unambiguously cometary with a clear coma and tail. No debates about whether it was a bare asteroid or something else. And crucially, 2I Borisov behaved like the comets we know. Spectroscopic observations revealed its composition water-dominated with carbon monoxide and cyanide, detected but as secondary components.
The gas production ratios matched what we see in Oort cloud comets. The dust-to-gas ratio was typical. The coma morphology, the outgassing patterns, the way brightness changed with solar distance, all familiar. 2I Borisov was weird because of where it came from, not because of what it was made of or how it behaved. It was a comet from another star system that looked and acted like our comets. That suggested something profound. Comet formation processes might be universal. The physics and chemistry that created the icy bodies in our outer solar system might operate similarly in other planetary systems. If true, that's profound. It means we can use our solar system as a representative sample that the comets we study tell us about comet formation everywhere. 3I Atlas challenges that assumption. 3I Atlas is weird because of both its origin and its chemistry. An 8:1 CO2 to water ratio doesn't match solar system comets. It doesn't match 2I Borisov. The extended water emission at large solar distances is unusual. The lack of non-gravitational acceleration despite substantial outgassing is anomalous. The possible nickel vapor detection adds a metallic component we rarely see. This suggests that different planetary systems or different regions within the same system produce different populations of comets. Formation conditions matter. Host star properties matter. Dynamical evolution matters. If you formed in a system with a low-mass star, a red dwarf that produces less heat and ultraviolet radiation than our Sun, your volatiles might have a different composition. If you formed in a binary star system where ultraviolet flux from a stellar companion irradiated the protoplanetary disk, surface processing might alter your ice ratios. If you were ejected from the very outer regions of a planetary system beyond where water ice dominates, your CO2 content might be unusually high. The point is, not all comets are created equal. The interstellar population likely contains vast diversity that our small sample size 2 or 3 objects can't yet characterize. 2I Borisov told us that some interstellar comets look like ours. 3I Atlas tells us that some don't. Both data points are valuable, but 3I Atlas is the one that forces us to expand our models. When Borisov was discovered, there was excitement, but relatively little controversy. Mainstream science welcomed it. Observations proceeded smoothly. Communications were straightforward. Here's an interstellar comet. It behaves like our comets. Fascinating confirmation that planetary systems elsewhere produce similar objects. With 3I Atlas, the reaction has been more complicated. The anomalies pile up. The uncertainties remain large. Speculative hypotheses gain traction, and institutional communication becomes more guarded. Why the difference? Part of it is the nature of the anomalies. Borisov required no special explanations. 3I Atlas requires multiple. And when you have to invoke special circumstances repeatedly to explain different aspects of the same object, you start wondering if you're missing something fundamental. Part of it is the involvement of high-profile scientists proposing unconventional hypotheses. Loeb has a platform credibility and willingness to explore ideas that make others uncomfortable. His engagement with 3I Atlas adds a layer of controversy that Borisov never had. And part of it is timing and context. We're in an era where public trust in institutions is fragile, where conspiracy theories spread rapidly, where scientific authority is questioned more than it has been in generations. Space agencies are navigating a communication landscape far more complex than in 2019. But here's what both Borisov and 3I Atlas teach us. Our sample size is still far too small to know what's normal for interstellar objects. 2 comets. 2 very different profiles. Are these representative of a vast diversity? Or are we seeing rare edge cases while typical interstellar comets remain undetected because they're fainter or less active? We don't know. And we won't know until we've studied dozens or hundreds of these objects. The Vera Rubin Observatory, when it becomes fully operational, will change that. Its wide-field survey capabilities and extraordinary sensitivity will detect interstellar objects that current telescopes miss entirely. Within a decade, we might have a statistical sample large enough to characterize the interstellar comet population properly. Until then, every new detection is precious. Everyone teaches us something. And everyone carries the possibility of surprise of being the object that doesn't fit, that forces us to expand our understanding, that reveals the universe to be stranger than we imagined. 2I Borisov was the familiar stranger, different origin, familiar nature. 3I Atlas is the true alien, different in origin and in essence. Both are invaluable. Both are temporary visitors carrying information we can never gather any other way. And both deserve better communication than they've received. September 7th through September 14th, 2025, the James Clerk Maxwell Telescope on Mauna Kea, Hawaii, tracked 3I Atlas through this week with its sub-millimeter receivers measuring emission from hydrogen cyanide HCN in the comet's coma. On September 7th, the measured HCN production rate was 1.5 hour 1025 molecules per second, plus or minus 50% uncertainty. 1 week later, on September 14th, that rate had climbed to 4.5 hour 1025 molecules per second. The production rate tripled in 7 days. That kind of rapid increase in outgassing activity is remarkable. It suggests the nucleus is responding dynamically to increasing solar heating as it approaches perihelion. But a tripling in 1 week implies something more than gradual warming of surface ice. It suggests structural changes, fresh material being exposed, new vents opening, possibly fractures propagating through subsurface layers. Comets are not uniform chunks of ice. They're agglomerations of material with complex internal structure, layers of different composition, pockets and voids, regions where ice has already sublimated, leaving behind porous dust. As a comet approaches the sun, surface layers heat up first. Ice begins sublimating, creating vapor pressure beneath the surface. That pressure can build until it fractures the overlying layers, suddenly exposing fresh ice that hasn't been weathered by space radiation or previous solar encounters. When fresh ice is exposed, outgassing rates spike. You see sudden brightness, increases changes in coma. Morphology shifts in gas composition ratios. These events, called outbursts, are common in comets and represent the nucleus's unstable response to solar heating. 3I Atlas's rapid HCN increase might be an outburst signature. Or it might be more gradual, the steady progression of the sublimation front moving deeper into the nucleus as surface reserves are exhausted. Either way, it tells us the nucleus is not a passive, static object. It's responding, changing, evolving under the influence of solar energy. The cyanide itself is interesting. HCN is an organic molecule, carbon, nitrogen, and hydrogen bonded together. It forms in cold molecular clouds, gets incorporated into cometary ices during formation, and survives if the comet never gets hot enough to destroy it. Detecting cyanide in comets isn't unusual.
But detecting it in high quantities with rapidly increasing production rates suggests this object has substantial reserves of organic material. That's consistent with formation in a cold environment rich in carbon-bearing molecules. The Very Large Telescope in Chile also detected cyanide in 3I Atlas's coma during late August observations, along with that puzzling nickel vapor signature. Those detections confirm the James Clerk Maxwell results and add confidence that we're seeing real chemical complexity in this object. By mid-September, when JCMT made its measurements, the coma had grown enormous. Estimates put its diameter at roughly 180,000 kilometers, significantly larger than Jupiter. The coma was also asymmetric, elongated along the anti-solar direction pointing away from the sun, which is exactly what you'd expect from a tail-forming mechanism where dust and gas are pushed by solar radiation pressure. This is where things get conceptually interesting. The coma of 3I Atlas is larger than most planetary diameters, yet it's composed of material from a nucleus that might be only a few kilometers across.
The nucleus mass might be measured in billions of tons, but it's creating a visible structure 100,000 kilometers wide. That's the power of sublimation. A tiny amount of material released as gas and dust can fill an enormous volume of space because the pressure is so low. 1 kilogram of water ice sublimating in the vacuum of space expands to occupy millions of cubic meters. The rapid activity increase suggests 3I Atlas was approaching a critical threshold in late September. Solar heating was becoming intense enough to drive subsurface processes, thermal stress, pressure buildup, structural failure. The nucleus was transitioning from relatively quiet to highly active, and this was still happening at distances around 2 AU from the Sun, farther out than Mars.
Most solar system comets don't become this active until they're inside 1.5 AU. 3I Atlas's early activity onset suggests either high volatile content or unusual internal structure that efficiently conducts heat to subsurface reserves, or both. This is speculation, but the pattern we're seeing, early activity onset, rapid production rate, increases extended water emission, could indicate a nucleus with high porosity. Porous structures allow heat to penetrate deeper more quickly. They also allow gas to vent from subsurface regions more easily, creating the kind of distributed activity we've been observing. If 3I Atlas is highly porous, that has implications for its formation. Porous structures form when material accretes gently without high-velocity collisions that would compact it. That's consistent with formation in the cold, distant regions of a protoplanetary disk, where velocities are low and gentle accretion dominates. But this is layering speculation on speculation. The truth is, we don't know the nucleus's internal structure. We can infer it from behavior, but multiple structures could produce similar observable effects. Science abhors ambiguity, but sometimes ambiguity is all we have. What we know for certain, 3I Atlas was becoming more active rapidly as it approached perihelion. Its outgassing rates were increasing on timescales of days to weeks. Its coma was enormous and growing, and the chemical complexity CO2 water cyanide, possibly nickel, was being maintained throughout this evolution. All of this is consistent with a natural comet responding to solar heating. Nothing here violates physics or requires exotic explanations. But the details matter, and the details keep pointing toward an object that's unusual in multiple independent ways. Active early, compositionally strange, structurally dynamic, large coma, rapid variability. Each of these is explainable, but together they paint a picture of a comet that doesn't fit neatly into the categories we've built from studying our own system's icy bodies. Maybe 3I Atlas is teaching us that our categories are too narrow, that the universe produces comets in varieties we haven't imagined, that every planetary system is a unique experiment in ice formation, and we're only now beginning to see the results. Or maybe we're missing something, some underlying pattern that connects all these observations in a way we haven't recognized yet. Either way, the interstellar visitor continues its dance with our sun, releasing its chemistry into space, giving us glimpses of a world we'll never see. We've traveled deep into the 3I Atlas story. We've examined chemistry orbits, outgassing size uncertainties, communication gaps. Now it's time to step back and assess, what are the most plausible explanations for what we're observing? Science works best when hypotheses compete on evidence, not on comfort. When we evaluate ideas based on how well they explain observations, how many new assumptions they require, how testable their predictions are. So let's lay out 3 tiers of explanation weighted by their support in evidence and mainstream scientific acceptance. Hypothesis 1: natural interstellar comet with unusual chemistry, 60% weight. This is the mainstream position supported by the vast majority of astronomers studying 3I Atlas. The argument: this is a natural comet composed of ice and dust that formed in another planetary system under conditions sufficiently different from our own that its composition and behavior appear unusual to us.
The high CO2 to water ratio is explained by formation in a cold, distant region of its birth system, perhaps 50 to 100 AU from the host star, where CO2 ice condensed more readily than water ice. Or, alternatively, by radiation processing during the system's early evolution that selectively removed water from surface layers. The large nucleus hypothesis resolves the acceleration mystery. If 3I Atlas is 5 kilometers or more in diameter, its mass 30-50 billion tons or more is sufficient that outgassing thrust produces acceleration below detection thresholds. Large objects don't get pushed around easily by gas jets. The extended water emission is explained by distributed sublimation of small ice grains carried far from the nucleus by more volatile gases. The rapid activity increase reflects normal thermal evolution as solar heating intensifies. The possible nickel detection suggests metal-bearing minerals in the nucleus, unusual but not unprecedented. Every observation fits within known physics. No exotic mechanisms required. The only specialness required is formation under conditions different from typical solar system comets, and given the diversity of planetary systems we're discovering around other stars, different formation conditions are absolutely expected. This hypothesis makes predictions post-perihelion trajectory should follow purely gravitational models. Orbit should remain hyperbolic with no signs of braking. Activity should gradually decline as the comet moves outbound and solar heating decreases. Spectroscopic observations should continue showing chemical signatures consistent with natural volatile sublimation. All of these predictions are testable with ongoing observations. If any fail, the hypothesis needs modification, but so far nothing has definitively falsified this interpretation. Occam's razor, the principle that simpler explanations requiring fewer assumptions are generally more likely, favors this hypothesis. It requires only that 1. Planetary systems vary in their formation conditions, and 2. 3I Atlas formed in one such variant system. Both are well-established facts. The weakness of this hypothesis. It requires invoking special circumstances where for multiple independent observations. Unusual formation location and large size and unusual internal structure. Each individually is plausible, but requiring all three simultaneously reduces overall probability. Still, this is the explanation most scientists accept as most likely given current evidence. Hypothesis 2. Extreme natural conditions, 25% weight. This tier represents explanations that remain natural. No violation of physics, no exotic new science, but invoke rarer conditions or edge cases that we've observed infrequently or never before. Perhaps 3I Atlas is a fragment of a larger differentiated body, a protoplanet or large planetesimal that broke apart during its home system's chaotic formation period. If so, it might contain materials from the parent body's interior metal-rich layers, unusual ice compositions, structural heterogeneity that produces unexpected outgassing patterns. Differentiated bodies form when objects grow large enough that internal heat from accretion energy, radioactive decay, or tidal heating melts the interior, allowing heavy materials to sink toward the center while light materials float upward. The result is layered structure, metal core, rocky mantle, icy crust. If 3I Atlas is a fragment from such a body, its composition might not reflect the pristine conditions of the protoplanetary disk. It might carry signatures of high-temperature processing, metal enrichment, chemical alteration that occurred deep inside a parent body that no longer exists. This would explain the nickel vapor metals from the core layers. It would explain unusual ice ratios. Surface layers wouldn't represent primordial disk composition, but rather recondensed volatiles from the parent body's disruption. It would also explain why the object is large and massive. Fragments from a shattered, differentiated body would naturally span a range of sizes, and kilometer-scale fragments would be common. Another edge case possibility. 3I Atlas spent its billions of years in interstellar space, passing through unusual environments. Perhaps it drifted through a molecular cloud where surface chemistry altered ice ratios. Perhaps it was exposed to cosmic ray flux densities higher than typical modifying surface layers, through radiation damage. Interstellar space is not uniform. It contains dense molecular clouds, low-density voids regions near supernova remnants with high radiation bow shocks where stellar winds collide. An object drifting for billions of years might encounter multiple environments, each leaving its mark on composition and structure. These are rare but natural scenarios. They don't require new physics, but they do require specific uncommon histories that we can't directly verify because we don't know where 3I Atlas came from or what path it followed to reach us. The weakness here is the same as Hypothesis 1, but amplified. We're stacking low probability events, fragment from differentiated body and ejection into interstellar space, and passage through unusual interstellar environments and arrival in our system. Possible, certainly. But each "and" reduces overall probability. This hypothesis also makes testable predictions, though they're harder to verify. If 3I Atlas is a differentiated fragment, its composition might show metal silicate fractionation patterns different from primitive comets. Deep spectroscopy might reveal mineralogical signatures of high-temperature processing. These are subtle signatures requiring excellent data, but they're distinguishable in principle. Hypothesis 3, artificial origin, 15% weight. Now we enter speculative territory. I need to be absolutely clear. This is not the mainstream scientific position. This is a minority hypothesis proposed by a small number of researchers, primarily Avi Loeb and colleagues. It is testable, it is falsifiable, but it requires extraordinary evidence, and we don't have extraordinary evidence yet. The hypothesis 3I Atlas is an artificial object, a spacecraft probe or artifact created by a technological civilization, using its volatiles as reaction mass for propulsion and navigation. The arguments supporting this interpretation: the lack of non-gravitational acceleration despite substantial outgassing could indicate controlled, balanced thrust rather than random venting. A spacecraft using multiple thrusters could produce zero net acceleration while still releasing propellant if the thrusters are fired in a way that cancels thrust vectors. The trajectory's low probability close approaches to 3 planets. Perihelion during solar conjunction could represent intentional navigation rather than chance. The timing of peak activity at perihelion could represent a propulsive burn, a reverse Oberth maneuver aimed at breaking into solar orbit. The chemical composition might represent propellant choice rather than natural formation. High CO2 content could be optimal for certain propulsion systems. These are testable claims. If 3I Atlas is artificial, it should show trajectory modifications after perihelion consistent with controlled propulsion. Non-random activity patterns, burns timed to orbital mechanics rather than thermal equilibrium, possibly electromagnetic emissions, heat signatures inconsistent with passive solar heating, or geometric structures resolved in high-resolution imaging. None of these have been observed yet. The trajectory, as of the most recent data, remains consistent with purely gravitational motion. Activity patterns follow thermal models. No anomalous emissions detected. But, and this is important, the critical test comes post-perihelion. If the orbit deviates from predictions in November-December 2025, if there are velocity changes unexplained by known natural mechanisms, this hypothesis gains weight. If no such deviations occur, if 3I Atlas continues outbound on its predicted hyperbolic trajectory, the hypothesis is falsified. The weakness of this hypothesis is obvious. It requires the existence of extraterrestrial technology, which we have never confirmed. It invokes an explanation that, while not physically impossible, requires vastly more assumptions than natural alternatives. Extraordinary claims require extraordinary evidence. The current evidence is interesting, but far from extraordinary. Anomalies exist, but anomalies are not proof of artificiality. They're proof that our models need refinement. Why include this hypothesis at all? Because scientific methodology requires considering all hypotheses consistent with observations, even uncomfortable ones. Because dismissing an idea without testing it is dogma, not science. Because even if this hypothesis is almost certainly wrong, the process of testing it rigorously is how we learn. And because vanishingly, improbably, but not impossibly, it might be right. And if it is, the implications would be profound beyond measure. Weighing the evidence. If I were forced to bet on which explanation is correct based on current evidence, I'd place 60% confidence on Hypothesis 1 natural comet, unusual formation, 25% on Hypothesis 2 natural but edge case, and 15% on the hypothesis I haven't even assigned weight to yet that we're missing something fundamental. Some explanation we haven't thought of because we don't yet understand the relevant physics or chemistry. Hypothesis 3 artificial gets perhaps 5% or less reserved for the possibility that extraordinary evidence emerges post-perihelion. But these are not fixed weights. They update based on new observations. Science is Bayesian. We adjust our confidence based on evidence as it accumulates. The next 2 months will shift these probabilities dramatically. Observations will either confirm that 3I Atlas is behaving as a natural comet should, or they'll reveal deviations that demand deeper investigation. Either outcome advances human knowledge. Either outcome is valuable. What's frustrating is that this evaluation, this careful weighing of hypotheses and evidence, is almost entirely absent from public communications about 3I Atlas. NASA's statements present a simplified narrative: interstellar comet, interesting chemistry, no threat. Which is true, but incomplete. The scientific community is actively debating these questions. Papers are being written. Conferences will feature discussions. Researchers are arguing about probabilities and interpretations, but that rich, complex debate isn't being communicated outward. And that gap between the vigorous scientific conversation and the sanitized public message is where trust erodes and speculation flourishes. 3I Atlas deserves better. The public deserves better. We all deserve a communication approach that respects both the complexity of the science and the intelligence of the audience. The universe is not obligated to be simple. Neither is the conversation about what we discover. Let's engage in a thought experiment, not prediction, not conclusion, but careful exploration of what different explanations would mean if true. Because science isn't just about collecting data, it's about understanding implications, following threads to see where they lead. If Hypothesis 1 is true natural comet with unusual chemistry, this means our solar system is not representative of comet populations across the galaxy, the comets we've studied for centuries. Halley-Hale-Bopp. The Jupiter family comets, the long-period Oort cloud objects, might be a local variation on a much broader theme. Formation conditions around other stars differ enough that some systems produce CO2-rich comets as commonly as we produce water-rich ones. Perhaps stars with different masses, different metallicities, different disk structures create different comet chemistries. This has profound implications for astrobiology. Comets are thought to have delivered volatiles, water-organic compounds, the ingredients for life to young planets. If comet composition varies widely depending on the host system, then the volatile delivery to planets varies too. A planet in a system that produces CO2-rich comets instead of water-rich ones receives different raw materials for potential life. That might make life less likely, or it might mean life there develops different chemistry, different biochemical pathways adapted to carbon dioxide as a primary volatile. We've been assuming Earth-like planets everywhere need Earth-like comet bombardment to become habitable. Maybe that's wrong. Maybe there are multiple pathways to habitability, each shaped by the particular comet population that system produces. For planetary science, this means our models need expansion. We've built our understanding of how planets acquire volatiles based on our solar system. But if other systems work differently, those models are local solutions to a universal equation we haven't fully written yet. For the search for life beyond Earth, we need to think more broadly about what habitable means. Water is essential for life as we know it, but life as we don't know it might thrive under different conditions, shaped by different volatile deliveries. This is exciting. It means the universe is more diverse, more creative, more full of possibility than we imagined. It means every new interstellar object that visits us is a window into a different experiment in planetary system formation. If hypothesis 2 is true fragment of differentiated body, this suggests large body collisions and disruptions are common in young planetary systems. We've inferred this from the architecture of our own system, the Moon, likely formed from a giant impact. Mars might have lost much of its mass in early collisions, but direct evidence has been sparse. Finding fragments of differentiated bodies drifting through interstellar space tells us that protoplanet-scale collisions not only happen but happen with enough frequency that ejected fragments populate the galaxy. That has implications for planet formation theory. Collisions are not rare edge cases, they're fundamental processes that shape final planetary architectures. The calm, ordered solar system we see today emerged from violent chaos we're only beginning to understand. It also means interstellar space is littered with the corpses of failed planets, asteroids and comets. Yes, but also fragments of bodies that almost became worlds, that had metal cores and silicate mantles and layered structure that were destroyed before they could evolve into mature planets. Every stellar system produces these fragments. Every system's violent youth scatters material into the void. And occasionally, by pure chance, those fragments cross paths with another system billions of years later. We are in a very real sense seeing the fossils of alien planetary systems. Dead worlds passing through. If hypothesis 3 were true artificial origin. Let's be clear, this is wildly speculative. The probability is low, but exploring implications is valuable even for unlikely scenarios because it clarifies what would constitute convincing evidence. If 3I Atlas were artificial, what would that mean? First, we are not alone, not just in the sense of microbial life on Mars or ocean worlds, but in the sense of technological civilizations capable of interstellar travel or at least interstellar object deployment. Second, interstellar travel is possible, whatever technological barriers. We imagine energy requirements, propulsion, physics, navigational challenges, another civilization solve them. Third, the galaxy might be more crowded than we thought. If we detect an artificial interstellar object in a sample size of 3 that suggests such objects are common enough that detection is not astronomically rare, the galaxy could have thousands or millions of these probes, most never coming near any star, drifting through the void on missions we can't fathom. Fourth, whoever sent it chose stealth or simplicity over communication. An object that looks like a comet that produces no obvious artificial signatures, that doesn't broadcast radio signals or respond to hails. It's designed to blend in, or it's simply a dumb probe collecting data passively. Fifth, they might be interested in us specifically or in stars like ours, or they might be indiscriminately surveying all systems. The trajectory that brings 3I Atlas near 3 planets could be intentional survey pattern or pure chance. Sixth, we need better detection methods. If artificial interstellar objects exist and look like comets, we're missing most of them. Current surveys detect only the brightest, most active objects. Stealthier or dormant ones pass unnoticed. But here's the thing. Even if this hypothesis were true, it wouldn't necessarily mean immediate contact or threat. An automated probe from a civilization that might not even exist anymore, sent millions or billions of years ago, would be archaeologically interesting, but not necessarily dangerous or communicative. It would mean we live in a galaxy that has been or is being explored. That somewhere sometime someone asked the same questions we're asking, what's out there, and sent proxies to find out. The common thread. Regardless of which hypothesis is closest to truth, 3i Atlas is teaching us humility. Humility about how much we understand. Humility about how representative our solar system is. Humility about the diversity of objects the universe produces. 3 interstellar objects. 1. Oumuamua was possibly a bare asteroid with tumbling rotation. 1 2i Borisov was a familiar-looking comet. 1 3i Atlas is strange in multiple ways. That's a 100% diversity rate. Every single interstellar object we've studied has been different from the others. What does that tell us? That our sample size is laughably small. That drawing conclusions from 3 data points is premature. That we need to remain open to surprise. The universe has been creative for 13.8 billion years. It's had time to produce outcomes we haven't imagined. Our theories built on observations of 1 planetary system and 3 interstellar visitors are sketches of reality, not final portraits. 3i Atlas. Whatever it ultimately is represents a gift, a chance to expand our thinking. A reminder that the cosmos is not obligated to conform to our expectations, and that reminder that intellectual humility might be the most valuable lesson an interstellar visitor can teach. Step back from 3i Atlas for a moment. Look at the broader picture of how scientific institutions communicate discoveries to the public. Because this isn't just about one object, it's about a relationship between science and society that's under strain. We're entering an era of unprecedented astronomical discovery. The Vera Rubin Observatory, when fully operational, will detect tens of thousands of near-Earth asteroids, hundreds of interstellar objects, countless transient events. The James Webb Space Telescope is revealing exoplanet atmospheres in detail we've never seen. Next-generation telescopes, the Extremely Large Telescope, the Giant Magellan Telescope. The 30-meter telescope will resolve features on distant worlds. Discoveries will come faster than we can fully process them, and each discovery will require communication to funders, to policymakers, to the public that supports these endeavors. How that communication happens matters enormously. Done well, it builds enthusiasm for science recruits. Future generations of researchers maintains public support for funding. Done poorly, it erodes trust, fuels conspiracy theories, and damages the social contract between institutions and citizens. 3i Atlas is revealing cracks in that communication system, not catastrophic failures, but stress fractures that could widen under pressure. The challenge space agencies face. They operate in a complex environment with competing pressures. Scientific accuracy demands careful qualification, acknowledgement of uncertainty, avoidance of premature conclusions. But public communication rewards clarity, simplicity, confident statements. Funding comes from governments and taxpayers who expect regular justification for expenditure. Press releases need to emphasize success, discovery progress. Admitting confusion or uncertainty can be politically risky. Media landscape rewards sensationalism. Headlines scream about alien possibilities even when scientists carefully hedge their statements. Agencies learn to be defensive to preemptively downplay anything that might generate overheated coverage. Professional culture values caution. Scientists who make bold claims that turn out wrong suffer career damage. Institutional pressures favor conservative communication that avoids risk. All of these are real considerations. None are malicious. But together, they create a communication strategy that defaults to managing information rather than sharing it transparently. What needs to change? Real-time data sharing with context. In the age of internet, there's no technical barrier to making observational data available publicly within days of collection, accompanied by explanatory materials that help non-experts understand what they're seeing. Imagine if JWST's 3I Atlas spectroscopy data had been released within a week of collection, with a live-streamed briefing where scientists explained the CO2 ratio, discussed possible interpretations, acknowledged uncertainties, and invited public engagement. That's technically feasible right now. Direct engagement with speculation. When unconventional hypotheses appear like Loeb's artificial origin idea, don't ignore them. Publish institutional responses that engage with the arguments. Explain why mainstream science favors different interpretations. Describe what evidence would be needed to shift that assessment. Treat the public as collaborators, not as an audience to be managed. Release the same information to everyone simultaneously. Explain the scientific process, the debates, the uncertainties, the competition between hypotheses. Show how science actually works, messy and iterative and self-correcting. International coordination. Space is humanity's common heritage. Discoveries made by one agency benefit all of humanity. Coordinate communication so there's a single authoritative source for information rather than fragmented statements from different agencies that may not align. Respect for public intelligence. The people most interested in stories like 3I Atlas are often highly educated, scientifically literate, capable of understanding nuance. Don't dumb it down. Provide depth. Trust that people can handle complexity. The precedent being set, how NASA and other agencies handle 3I Atlas will influence how they handle the next anomalous discovery. And the next. And the dozens or hundreds that will come as our detection capabilities improve. If the pattern is silence on hard questions, simplified press releases, slow data releases, and defensive avoidance of speculation, we're in for a decade of public confusion and institutional distrust. But if agencies use this as an opportunity to experiment with better communication, with transparency, real-time engagement, honest acknowledgement of uncertainty, they could build a foundation of trust that carries forward. The choice is theirs. But the consequences affect all of us, the broader context. This isn't just about astronomy. It's about how society handles scientific uncertainty in an era when so much is uncertain. Climate change, pandemic response, technology regulation. Almost every major policy question touches on scientific knowledge that's complex, evolving, and uncertain. The public needs to develop comfort with scientific uncertainty, understanding that "we don't know yet" is a valid and honest answer, not a failure. Space agencies have an opportunity to model good science communication for other fields, to show that you can be rigorous and transparent simultaneously, that uncertainty is strength, not weakness, that the public can be trusted as partners in discovery. 3I Atlas is a test case, a relatively low-stakes object, no danger, no immediate policy implications, where experimentation with communication approaches carries little risk. It's a chance to do better. So far, that chance is being missed, but there's still time. Post-perihelion observations are ongoing. Data is being collected. Analyses are proceeding. Public interest remains high. What happens next, how information flows from scientists to citizens over the coming weeks, will set precedent for years to come. The interstellar visitor isn't just testing our instruments and models. It's testing our institutions and our commitment to transparent communication. How we respond to that test matters more than we might realize. It's early November 2025 as I write this. 3I Atlas has passed perihelion. It has rounded the sun and begun its journey back toward interstellar space. The solar conjunction period is ending. Ground-based telescopes can observe it again. The next 60 days are critical. They will answer questions that have been building for months. They will test the hypotheses we've discussed. They will either confirm 3I Atlas as an unusual but natural comet, or they will deepen the mystery in ways we can't yet predict. What are astronomers watching for trajectory deviations? Astrometry precise measurement of position will reveal whether the orbit deviates from purely gravitational predictions. If there are velocity changes unexplained by known forces, if the orbit shows signs of braking or course correction, that would be extraordinary. Natural comets don't do that. Controlled spacecraft might. The arcs of paper predicted that optimal timing for establishing an Earth approach trajectory would occur in late November to early December. That prediction is testable. If nothing unusual happens, if the orbit remains purely gravitational, the artificial origin hypothesis is effectively dead. Activity evolution. Is outgassing continuing at the rates observed pre-perihelion? Is it declining as expected as solar heating? Decreases, are there sudden outbursts or changes in coma morphology that would indicate structural instability? Natural comets typically show declining activity as they move away from the sun. The sublimation rate depends on temperature, and temperature depends on solar distance. If 3I Atlas maintains unexpectedly high activity levels while moving outbound, that would require explanation. Spectroscopic changes. Is the chemical composition shifting? Are different volatiles dominating at different distances, suggesting layered structure? Is the CO2 to water ratio changing or remaining constant? Monitoring gas production rates and ratios as the comet moves outbound provides insight into internal structure. If surface layers have different composition than deeper layers, we'd see that reflected in changing spectra. Fragmentation. Some comets break apart under thermal stress or tidal forces. 2I Borisov showed signs of possible fragmentation near perihelion. If 3I Atlas fragments, we might suddenly see multiple components in the coma, changes in brightness distribution, or even separate nuclei. Fragmentation would be scientifically valuable, exposing fresh interior material, providing natural cross-sections through the nucleus structure, but it would also make interpretation more difficult. Brightness evolution. Is the comet fading at the expected rate based on increasing distance, or is it maintaining brightness levels that would indicate continued high activity or unusual light scattering properties? By early December 2025, 3I Atlas will be visible in the morning sky for observers at northern latitudes moving through the constellation Leo. Amateur astronomers with good equipment can contribute observations. Professional observatories will track it continuously. By late January 2026, it will drop below magnitude 12, becoming too faint for most amateur equipment, but still accessible to professional facilities. Observations will continue as long as feasible, potentially into mid-2026, before the comet fades completely. Every observation adds data. Every data point constrains models. By the time 3I Atlas vanishes from our ability to observe it, we'll have months of post-perihelion data to analyze. That data will tell us whether this object is simply an unusual natural comet, weird chemistry, large size but ultimately explainable, or whether something more puzzling is occurring. The Europa Clipper and Hera possibilities. Both spacecraft launched in 2024 have trajectories that might intersect with 3I Atlas's coma or tail during November-December 2025. If that intersection occurs and instruments are available, we could get direct sampling of interstellar cometary material. That would be unprecedented. We've never sampled material from outside our solar system. The data particle composition, isotopic ratios, organic compound analysis would provide insights we can't get from remote spectroscopy. But as with so many potential observations, we don't have confirmation that these opportunities will be taken. No announcement from NASA or ESA, no published observation plans, just speculation based on trajectory calculations that suggest the opportunity exists. The broader timeline. November 2025 intensive observation campaign as comet emerges from solar conjunction. Astrometry to measure position precisely, spectroscopy to track activity, photometry to monitor brightness. December 2025 continued tracking. By mid-month, closest approach to Earth at 1.8 AU, still very far but geometrically favorable for observation. Amateur observers can participate. January 2026, comet fading but still observable.
Activity should be declining noticeably as solar distance increases and temperatures drop. February-March 2026, approaching Jupiter. Close approach on March 16, 2026 at 0.36 AU 54 million km². NASA's Juno spacecraft orbiting Jupiter might observe if fuel and mission constraints allow, April 2026 onward. Continuing outbound. Gradually fading beyond observability. By mid-2026, only the largest telescopes will be able to track it. Eventually, it vanishes, and then it's gone. Back into interstellar space on a trajectory that will carry it out of our solar system over decades and centuries. Perhaps it will encounter another star in a few million years. Perhaps it will drift forever between stars. We'll never know. This is our one chance, our brief window to study a visitor from beyond.
What if the data is ambiguous? Here's the scenario that concerns me most. What if 3i Atlas does something unexpected but subtle? What if the orbit deviates slightly from predictions but not so dramatically that natural explanations can be ruled out? What if there's a small velocity change that could be interpreted either as asymmetric outgassing or as controlled propulsion? We'd be left with dueling interpretations. Mainstream astronomers would favor natural explanations, arguing that cometary outgassing is complex and can produce unexpected trajectory perturbations. Loeb and others would argue the deviation supports their hypothesis that the probability of natural processes producing that specific effect is low. Both sides would have legitimate arguments. Neither could definitively prove their case. We'd be stuck with ambiguity, the worst possible outcome for public understanding, because ambiguity breeds conspiracy theories. When experts disagree and data is inconclusive, people fill the gap with their own interpretations, often influenced by pre-existing beliefs rather than evidence. If that happens, if we end up with ambiguous data and competing interpretations, NASA's communication strategy will be tested severely. Will they engage transparently with the debate, presenting both sides fairly and explaining why uncertainty persists? Or will they default to the simplified message, picking one interpretation and downplaying alternatives? I hope for the former. I expect the latter. And that expectation is based on everything we've observed about how 3i Atlas information has been communicated thus far. The personal reflection I've spent months following this story. Reading papers, analyzing data, watching how information flows from scientific literature to press, releases to public discourse. And I'm left with a complex mix of feelings. Excitement about the science. 3i Atlas is genuinely interesting, regardless of what it turns out to be. Every interstellar object teaches us something new. Frustration about the communication. The gap between what scientists know and what the public is told has been consistently large. Hope that this can improve, that space agencies will recognize the need for better transparency and adapt their approaches, and profound wonder at the simple fact that we live in an era where we can detect and study objects from other star systems. That capability, which would have seemed like magic to previous generations, is now routine. We are living in the golden age of astronomy. Discoveries are accelerating. Technology is advancing. The universe is revealing itself in ways we never imagined. But that golden age will only reach its full potential if the discoveries are communicated well. If institutions trust the public. If science remains accessible and transparent. 3i Atlas is still out there right now, moving away from the sun, carrying its secrets. In a few weeks, we'll know more. In a few months, the story will have its next chapter, and somewhere in that story, in the data yet to be collected, the analyses yet to be completed, the papers yet to be written, lies an answer to what this interstellar visitor truly is. The universe is patient. It doesn't hurry. It doesn't care about our timelines or our curiosity. But we care, and so we watch, and we wait. and we hope that when the answer comes, we'll be wise enough to understand it and honest enough to communicate it. The stars have been sending us messages for billions of years. Most go unread, photons arriving after journeys across light years, carrying information we don't yet know how to decode. But sometimes, rarely, a message arrives in a form we can grasp. A piece of another world delivered to our doorstep by the galaxy's vast and patient postal service. 3i Atlas is such a message, formed around a star we cannot name in a system we will never see, shaped by forces that played out when our Earth was young or not yet born. Ejected by gravitational violence by the chaotic dance of planets, finding their orbits by processes we model but have never witnessed. Drifting for eons through spaces so empty that matter is measured in atoms per cubic meter, through cold so profound that chemistry nearly stops, through darkness lit only by the faint glow of distant stars, until by pure geometric chance its path intersected ours, until our sun's gravity bent its trajectory inward, until we clever primates with telescopes noticed a faint point of light that moved too fast and came from too far. What have we learned? We've learned that this visitor carries chemistry unlike anything in our solar system, an 8-to-1 CO2 to water ratio that breaks every model that points toward formation conditions we've never seen in our own cosmic neighborhood. We've learned that it releases gas without showing the acceleration we expect, that it's either more massive than we can easily explain, or structured in ways that produce perfect thrust cancellation, or speculatively controversially doing something we don't fully understand. We've learned that its trajectory brought it near 3 planets in a sequence that occurs in perhaps 1 in 200 to 1 in 2,000 interstellar visitors. Unlikely but not impossible, notable but not necessarily meaningful. We've learned that it became active early, that water emerges from unexpected distances in its coma, that cyanide and possibly nickel vapor speak to chemical complexity we're still parsing, and we've learned that uncertainty persists, that months of observation with humanity's best instruments haven't resolved fundamental questions like how large the nucleus is, how massive it might be, whether it's a pristine comet or a fragment of something larger. But perhaps most importantly, we've learned something about ourselves, about how we communicate discovery, about the gap between scientific knowledge and public understanding, about institutional caution and the need for transparency. 3i Atlas came from the stars, but the story of how we've reacted to it, how we've studied it, debated it, communicated about it, that story is entirely human. What we know for certain, 3i Atlas is interstellar. It came from beyond our solar system, from somewhere in the vast galactic beyond. That is established beyond doubt. Its chemistry is unusual. The CO2 dominance, the chemical complexity, the activity patterns all deviate from what we see in typical solar system comets. That is observed fact.
Several characteristics don't fit standard models. The lack of non-gravitational acceleration, the extended water emission, the rapid activity changes each requires explanation, and the standard explanations require invoking special circumstances. More data is coming. Post-perihelion observations will continue through early 2026. Trajectory measurements will reveal whether the orbit deviates from gravitational predictions. Activity monitoring will show whether behavior remains consistent with natural comet models. What remains unknown, the nucleus size and mass. Despite months of observation, uncertainty spans more than an order of magnitude. We don't know if we're looking at a 500-meter boulder or a 5-kilometer mountain. The internal structure. Is it a pristine comet, a differentiated fragment, something in between? We can infer from behavior but not directly observe whether it will do anything unexpected post-perihelion.
The orbit might continue as predicted, confirming natural origin, or it might show deviations that deepen the mystery. How common objects like this are. Is 3i Atlas typical of interstellar comets or an outlier among outliers? Our sample size is too small to say. The honest position science doesn't have all the answers yet. That's not failure. That's the nature of discovery. We're watching a mystery unfold in real time, gathering data, testing hypotheses, updating our understanding as evidence accumulates. The most intellectually honest statement anyone can make about 3I Atlas right now is, we're not sure, and here's why the uncertainty persists. That's not satisfying for those who want definitive answers. But it's true. And truth, even uncertain truth, is more valuable than false confidence. The gap between data and understanding. There's a space between what we observe and what we understand. A space filled with models, interpretations, competing hypotheses. That space is where science happens, where observation meets theory, where ideas are tested, where understanding gradually emerges from confusion. For 3I Atlas, that space remains large. We have data, we have observations, but the synthesis, the coherent explanation that ties everything together, hasn't fully formed yet. Maybe it never will. Maybe this visitor will remain partially mysterious, leaving us with a collection of well-established facts that don't quite fit into a satisfying narrative. That would be frustrating, certainly, but it would also be instructive because mystery is often the universe's way of telling us our concepts are incomplete. What NASA isn't telling us. Perhaps what they're not telling us is simply what they don't yet know. Perhaps the communication gap exists not because of conspiracy or cover-up, but because institutions struggle to communicate uncertainty effectively. Saying, "we don't know," feels like admitting failure. But it shouldn't. It should be a statement of process: we don't know yet, but we're working on it, and here's what we're doing to find out. If that honest uncertainty were communicated transparently, if press releases said, "here are 3 competing explanations and why we can't yet distinguish between them," trust would grow, not diminish. The conspiracy thinking that surrounds 3I Atlas doesn't emerge from hidden data. It emerges from the perception that data is being hidden. And that perception is fed by communication strategies that prioritize simplicity over complexity, certainty over honesty, management over transparency. NASA could change that perception overnight, not by revealing secret knowledge there isn't any, but by communicating openly about what's known, unknown, and debated. The larger meaning, 3I Atlas, reminds us of our place in the cosmos. We are residents of one planetary system among hundreds of billions in our galaxy. We've studied our local neighborhood intensively, but we've barely glimpsed what exists beyond. Every interstellar visitor that passes through is a gift, a free sample of conditions elsewhere delivered, without the need for expensive interstellar missions we can't yet build. We should treasure these opportunities. Study them comprehensively, communicate about them honestly, and remain humble about how much we have yet to learn. The universe has been conducting experiments for 13.8 billion years, creating stars, assembling planets, sculpting comets, shaping the vast diversity of cosmic environments we're only beginning to survey. Our theories, built on observations of one system and a handful of visitors, are first drafts, sketches, preliminary models that will need revision as more data accumulates. That's exciting, not discouraging. It means discovery awaits. It means the story is just beginning. The open question. As 3I Atlas vanishes back into the cosmic dark, carrying with it the chemistry of another world, we're left with a question that won't let go. What else is out there moving through the void that we haven't yet learned to see? How many other visitors are passing through our solar system right now, too faint or too fast or too stealthy for our current instruments? How many messages from other worlds are being delivered that we're not yet equipped to read? And when the next visitor arrives, because it will arrive, the galaxy is patient and probability is relentless. Will we be wiser in how we study it, more honest in how we communicate about it, more open to being surprised by what it teaches us? That question remains unanswered. But the universe is listening.
And somewhere in the darkness between stars, another messenger is already on its way. Sleep well, curious minds. The stars are not done sending us their stories.